us is made up of matter, which is composed of atoms that cannot be seen by the human eye. To see atoms, X-rays, which have much smaller wavelengths than visible light, are needed. Other invisible radiations like ultraviolet and infrared rays are useful for studying vibrations of atoms in molecules. Laboratory-based experiments to probe atomic scale phenomena are often limited by lack of sufficiently bright and tunable sources of these radiations. The synchrotron radiation source, which is one of the marvels of modern science, produces highly intense radiation spanning the entire range of visible as well as invisible wavelengths. What is synchrotron radiation? When any charged particle like an electron is accelerated along a circular path by the action of a magnetic field, it emits what is known as dipole radiation. When the speed is increased till it is close to the speed of light, an extremely bright and well-directed radiation is emitted. The machines used to accelerate electrons to such high speeds are called synchrotrons, and the emitted light, which contains all wavelengths from infrared to X-rays, is called synchrotron radiation. In a synchrotron radiation facility, electrons emitted by an electron gun are first accelerated in a microtron or linear accelerator, after which they enter a circular accelerator called a booster synchrotron. Here, the energy of the electron is boosted up to high speeds, approaching the speed of light. Next, the electrons are injected into a storage ring made up of alternate straight sections and curved sections, consisting of different types of magnet arrangements. In the storage ring, they circulate at a constant speed for several hours or even days. The emitted radiation is used for different types of experiments. Over 50 light sources are in operation all over the world, including the Indian synchrotron radiation sources Indus 1 and Indus 2 at the Raja Raman Center for Advanced Technology at Indore. Scientists from physics group of Bhabha Atomic Research Center have set up several experimental facilities at Indus 1 and Indus 2. The fundamental parameters used to probe the physical world have given rise to various experimental techniques. For example, in photoelectron spectroscopy, X-ray photons knock out electrons from the sample. By measuring the energies of these electrons, valuable information is obtained about the energy levels of the atoms in the sample. In X-ray diffraction, incident X-rays are scattered from the sample and interfere with one another to form a diffraction pattern. By analyzing this pattern, scientists can reconstruct the structural arrangement of atoms within the material. Today, synchrotron radiation is widely used for scientific research in diverse fields. A number of groundbreaking discoveries were rendered possible only with the advent of synchrotron radiation. Several Nobel Prizes have been awarded in the area of synchrotron science and technology. Recently, the structure and interactions of proteins linked to COVID-19 have been solved using synchrotron radiation. Truly, the use of synchrotron radiation as a light source has revolutionized modern scientific research.
synchrotron radiation is omnipresent in the universe. It is produced when highly energetic charged particles such as electrons and protons spiral around magnetic field lines at a constant speed, and it spans over the entire electromagnetic spectrum ranging from radio waves to gamma rays. Energetic particles are produced in different corners of the universe by some processes still unknown to mankind. When energetic particles enter the magnetic field of Earth, they produce geosynchrotron radiation in radio band. Up in the sky, heavenly objects emit much of their energy through synchrotron radiation. In our Milky Way galaxy, rotating neutron stars with very strong surface magnetic field are born after supernova explosion. Produce pulses of synchrotron radiation due to the spiraling electrons in their surface magnetic field. Beyond the Milky Way galaxy, gigantic jets powered by supermassive black holes at the center of different galaxies show their presence through synchrotron radiation. Atomic Research Center has set up one of the largest gamma-ray telescopes, MACE, at highest altitude in Hanle, Ladakh, to probe the high-energy processes related to synchrotron radiation from various sources in the universe.
Invitees, dear students, and all those who have connected through internet. I am Himal Bhatt, and on behalf of Bhabha Atomic Research Center, I thank you all for joining us in celebrating the National Science Day. To start the proceedings, may I now request Associate Director Physics Group of BARC, Dr. S.M. Yusuf, to kindly escort the dignitaries to the dais. I request Associate Director Physics Group, Dr. S.M. Yusuf, to kindly felicitate our dignitaries. I request Dr. Alka Garg to kindly felicitate the Associate Director Physics Group. I now request Dr. S.M. Yusuf to kindly give the introductory remarks.
Respected Dr. R. Chidambaram, Homi Baba Professor, former Chairman, Atomic Energy Commission of India, and Principal Scientific Advisor to Government of India. Dr. K.N. Vyas, present Chairman of Atomic Energy Commission of India, Dr. A.K. Mahanti, Director, Bhabha Atomic Research Center, distinguished members of Bombay Council of Bhabha Atomic Research Center, other colleagues, distinguished speakers, principals and teachers of the participating schools and colleges, and the large number of eager and enthusiastic students participating online. A very good morning and welcome to all of you to this National Science Day celebration, NSD 2021. Every year, National Science Day is celebrated in India on 28th of February, commemorating the discovery of the Raman effect by Sir C.V. Raman on 28th of February in 1928, for which he was awarded the Nobel Prize in the year 1930 in physics. Dear students, as you are aware that when white light, let us say, which emits from sunlight, when it falls on a prism, due to the dispersive power of the prism, what you finally get, the 7 colors. So this tells you that the sunlight, white light is nothing but it is consists of 7 colors. But at Indian Association for the Cultivation of Science in Kolkata, what Professor C.V. Raman and his students, particularly I take the name of Dr. K.S. Krishnan, what they observed that even when a monochromatic light with single wavelength is scattered by certain molecules or the group of atoms due to their vibrations, they not only give the scattered wavelength of the same, which is incident, but there are other wavelengths which is lower and higher, and they are symmetrically placed with respect to the incident wavelength, with respect to their wavelength shift. So this great discovery is known as the Raman effect, and for which the Physics Nobel Prize was given to Sir C.V. Raman, and he is the first Asian to receive Physics Nobel Prize, and that was in the year after 2 years, 1930. So it was a brilliant and surprising discovery. So it was Professor C.V. Raman's deep knowledge in physics and innovative mind and devotion to work that helped him to get the Nobel Prize. Of course, Professor Raman and his students, they were very much aware of the limitation of the light source, the brightness of the light source, and as you know, in 1960s, lasers were available, so that could compensate. And his today's theme of this National Science Day is Synchrotron Science and Technology, where you will see how much bright light one can expect from this synchrotron light. My dear students, I'd like to bring out some facts in front of you, so to inspire your young minds and to get lessons from it. Professor C.V. Raman, he got educated entirely in India, and he passed his BA in physics, winning the first place and also the gold medal from the Presidency College in Madras. After that, after completion of his MA in physics, he got this Indian Civil Service job and moved to Calcutta at that time in 1907. So that time he was working very, very hard, and after hours he was doing the research at the cultivation of Indian Association for the Cultivation of Science, and that time his interest was the acoustics, the sounds, because he was fond of musical instruments which are made of strings. And he made very pioneering contributions during that almost first 10 years when he was working almost alone, and he published nearly 27 papers almost alone, and that made the IS, Indian Association for the Cultivation of Science, to become recognized as a vibrant research institute. And at the age of 29, that is in 1917, he resigned from the lucrative civil service job, and then when the Professor Sir Ashutosh Mukherjee, the then Vice Chancellor of Calcutta University, offered him the Palit Professorship of Kolkata, and that time the Indian Association for the Cultivation of Science was the research wing of Calcutta University, and he started doing full-time research. And initially, as I said, he was working on acoustics, and then he moved from the acoustic branch to the branch of scattering of light. But he was already very well known by the time, and I would like to mention that when he visited London in 1921, so his reputation was so high in optics and especially in acoustics that he was received by well-known physicists at that time, the English physicist Sir J.J. Thomson and Lord Rutherford. You have come across these two scientists' names in your textbook, I'm sure. And in the year of discovery, 1928, when the Raman effect was discovered, so in his lab, there are 32 research workers, and out of them, 21 were full-time. So he built a homemade spectrometer for doing the light experiments, and at that time, there is an article initiated by INSA that cost of that instrument has been calculated. That time it was rupees 7,630 rupees, and considering the 1 pound, Great Britain pound equivalent to 10 rupees. So, in fact, while he was doing masters in the Presidency College in Madras, that time at the age of 18, he published his first paper and that was published in philosophical magazines. And for his Nobel work, on which he got Nobel Prize, he first published in Indian journal. And in fact, now also Cultivation of Science continues that journal. And later on, of course, he published in very famous paper, a famous journal, that is Nature. So, I am just telling you all these historical events. I'm sure this will ignite your scientific mind, and we hope that during this today and next 2 days, your inner scientific mind will be shined by the bright light which will emit from your computer screen of the synchrotron. I also hope, like the polarized property of the synchrotron light, your scientific mind will be polarized in the right direction. So it will polarize your scientific thought processes. And like the synchrotron radiation, which gives us the broad wavelength range, and I am sure this 3 days program will enhance your knowledge and it will be broaden your scientific knowledge. So our program will be successful if this 3 days program can ignite your young minds and some young Chandrasekhar is born. India looks at you. India needs many more Professor Sir C.V. Raman. So we hope you will be mesmerized by the experience of the advancement of the science and technology which you will go through over these 3 days. With this, I end my introductory remark. Thank you and Jai Hind.
Thank you very much, sir. I now invite Director BARC, Dr. A.K. Mohanty, to give the welcome address.
Respected Dr. Chidambaram, Hamibaba Chair Professor, Dr. K.N. Vyas, Secretary DI and Chairman AEC, Dr. Yusuf, Associate Director of Physics Group, Professor Basudhab Rao, Vice Chancellor HBNI, TC members and my colleagues, dignitaries present here, as well as those of you participating remotely, and my dear students. Good morning to all of you. It is my pleasure to welcome you all to this Festival of Science, which we celebrate on National Science Day every year. Dear students, as told by Dr. Yusuf just now, this day is celebrated to commemorate the discovery of Raman effect, which is one of the greatest discoveries in modern science made by Sir C.V. Raman. This is the effect which explains why our sky looks blue. In a scientific terminology, it is a wavelength changing inelastic scattering of light from the molecules or atoms that gave birth to a wonderful Raman spectroscopic tool to gain information about different materials and their tendency to scatter light. Traditionally, Raman spectroscopy relies on the study of inelastic scattering of light, usually from a laser in the visible, near infrared and ultraviolet range. However, in recent times, its application has been extended to exterior region as well. Therefore, this year's theme will introduce you to a new type of radiation that comes out from a synchrotron machine. This synchrotron radiation, which is produced due to the bending of an energetic electron beam, although invisible and lies in the X-ray region, is a very powerful tool to study various materials properties for different applications. As you will all see in the presentation in this event, the science that generates the synchrotron light, the technology that makes it possible, as well as the application for research, is both fascinating and inspiring. My colleagues at Bhabha Atomic Research Center, working in basic research of physics, chemistry, biology, as well as in various engineering disciplines, strive to generate new knowledge and ideas aimed at being self-reliant or Atmanirbhar in nuclear and other related technology. The BRC beamlines at Indian Synchrotron of Indus 1 and 2 at Rajaramana Center for Advanced Technology, Indore, is a striking example of this. In the ensuing lectures, you will all have a chance to directly interact with the eminent scientists for learning about science and technology of the synchrotron, covering how the machine is built, how it produces radiation, and its applications. Without taking much of your time, once again I welcome you to this program and hope you all will take complete advantage of it. Jai Hind and thank you.
Thank you very much, sir. I now request Chairman Atomic Energy Commission and Secretary to the Department of Atomic Energy, Dr. K.N. Vyas, to kindly release the booklet of NSD 2021, followed by his inaugural address.
Thank you very much. Dignitaries, this is the mic. Okay. Thank you. Dignitaries on the dais, respected Dr. Chidambaram, chief guest for today's function, Dr. Mohanty, Director BRC, Dr. S.M. Yusuf, Director Physics Group, Professor Vasudev Rao, so many members from Bombay Council, many other senior colleagues, young students watching online, ladies and gentlemen. It is my pleasure to be delivering the inaugural address of National Science Day 2021 celebrations. It is a welcome sign that today we are holding this inaugural function in a physical gathering, although with very limited audience as I see, and it is good we are following the directives by the local government. But it's an indication that the pandemic is tapering off and we are gradually trying to normalize our lives. Despite the spike that we observe, I am sure this is going to pass over and we will be able to come back to more or less our normal lives. But at this time, we must remember that there is a still long way to go before we can consider ourselves to be completely safe, and therefore all the succeeding events, it is very nicely organized that they are in the virtual space. About the National Science Day, it has been very nicely mentioned by Dr. Yusuf, but I would like to remind again here that National Science Day, this has been conceived as a celebration of scientific achievements of the nation, which are showcased in the form of science exhibitions or displays, workshops, seminars, symposia, and other similar scientific activities in the educational and research institutes all over the country. This serves the purpose of bringing awareness to the common man regarding the contribution of science and technology in our daily lives. The development of a vaccine for the coronavirus within a short span of 1 year bears ample testimony of to emphatically reinforce this fact. The event further fulfills the objective of inspiring and motivating young minds to pursue exciting careers in scientific research. DAE has been at the forefront of some cutting edge research programs in physical, chemical, and biological sciences, and it is a magnet which draws young researchers to its fold for its reputation, facilities, research infrastructure, and the scientific culture that has been created within the organization. We have chosen different topics in the past as a specific theme every year. If I recollect correctly, BRC has selected various themes in the past and showcased its capability in the areas of physics, chemistry, material science, accelerated technology, electronics and computer science, front-end nuclear fuel cycles, etc. And I'm happy to note that for this year the theme is synchrotron science and technology. One of the premier DAE Research Institute, Raja Ramana Center for Advanced Technology, RRCAT, Indore, is housing one of its kind synchrotron facilities. As has been brought out very nicely in the film which was shown, and I would not like to point out the errors which I have in my written down script. I will not repeat that. But at the same time, I would like to emphasize here that RRCAT, which is housing Indus 1 and Indus 2, both of which are operational. It has been used by universities, researchers from BRC, and of course many researchers from the industry. Now, with experts in the physics group and specifically Dr. Chidambaram and Dr. Mohanty sitting here, I would deviate a little bit from my written down speech, and I will like to mention about one article which was given to me by most likely Dr. Sahu, and the work which was carried out under the guidance of Dr. Chidambaram related to Rasa Sindur. I must admit, if I recall it clearly, it was having an investigation of the Ayurvedic medicine, which was investigated using synchrotron radiation, and most likely I think the technique used was XFs. I will tell you why I read that with interest, and still I could not understand any aspect in this. My grandfather always used to say that when we try to take Ayurvedic medicine, try to avoid taking these Bhasma medicines. And I found a proof of this particular whatever experiment that was, I would say, carried out under guidance of Dr. Chidambaram is the procedure for making the Bhasma medicines are supposed to be extremely complex, and it has to be very religiously followed. Like, you cannot increase the temperature and then you say that I will do it faster. If certain thing has to be dried in the sun and then once again it has to be crushed once again and dried in the sun, that also should be done. There are no shortcuts possible. And what I recollect is that using that experiment, several brands were selected, and some of them were having mercury, which is supposed to be very poisonous material. The mercury in certain preparation, it was found to be inactive. It was not supposed to be harming the body, while in the other form, what I recollect after having read that paper, is that may not be conducive to good health. So I would try to sort of bring out this particular thing, that there is a way of looking at ancient medicine using modern tools, and it may give us some revelation, and which is where I feel we should try to sort of collaborate with each other. So, dear friends and colleagues, the country is well aware of the scientific and technological prowess of DA in the spheres of nuclear science and technology, augmented by cutting-edge science research in various other domains. These achievements have been possible largely due to the inspired and tireless effort of our scientists and engineers who form the backbone of our programs. We induct young scientists and engineers every year into our organization at all levels. Participation of a large number of school and college students in this event is therefore highly welcome, and I hope this will inspire many young students to take up an exciting and fulfilling career in scientific research, not only in DAE, but in various other scientific organizations of the country. I would like to take the opportunity to compliment the organizers for putting together this event despite constraints, and I am sure that large online participation will serve the objectives of celebrating the National Science Day in the country. As I end, I may recall that during the past year, major discussions have been related to COVID-19 and development of vaccines. So far as vaccines are concerned, it is acknowledged that Louis Pasteur was the person who had created first set of vaccines, specifically for rabies. I would like to mention a very cryptic quotation by him, which is relevant for all the fields of science. And I quote, "In the fields of observation, chance favors only the prepared mind," unquote. Many a times it has been mentioned that discoveries take place due to a chance. However, the quotation by Louis Pasteur highlights importance of experimentation and extensive preparation necessary for the same. Synchrotron radiation is one such experiment which will open up large avenues or large knowledge base that is still hidden from us. Thank you very much. Jai Hind, and for this specific occasion, Jai Vigyan. Thank you.
Thank you very much, sir, for this motivating speech, which will immensely benefit not only the students but also the researchers. Dear students, may I now request all of you to join us in welcoming our chief guest, Dr. R. Chidambaram, former Principal Scientific Advisor to Government of India, former Chairman, Atomic Energy Commission, and currently DAE Homi Bhabha Chair Professor, to deliver the keynote address.
Dr. Vyas, Dr. Mohanty, Dr. Yusuf, distinguished members of the audience, where I'm very happy to see Dr. Vasudev Rao, friends and colleagues. I'm very happy to participate in this National Science Day function, and I'm grateful to Dr. Yusuf for inviting me here. You heard, of course, the focus in this meeting is going to be on synchrotron radiation sources, and you saw some beautiful movies prepared by physics group, which small movies which are beautifully done, explaining the principles of synchrotron radiation, and also we had excellent introductory talks by Dr. Vyas, Dr. Mohaddi, and Dr. Yusuf. Interestingly, you mentioned about Rasa Sindoor. You know, Rasa Sindoor, like Brahmi, is a wonder drug in Ayurveda. And when I was the principal scientific advisor, I had started a project on science in Ayurveda. Exactly what you said. Apply modern principles to explain. Efficacy is known, but can we establish the science behind it? And the way we took up this young scientist, the high pressure physics group took up a lady scientist, Rasa Sindor. I had met Mr. Dalai Lama on a holiday, and he told him, up with the conversation came to science, and he told me that the British scientists had taken samples of his hair to London and found a lot of mercury in it, and mercury is toxic according to. So he said, but I'm healthy and my Guruji was healthy, so please find out why mercury in Tibetan medicine and in Ayurveda, Rhizosindura contains mercury, is not toxic. And that is how, and Arya Vaidyashala, we got some samples of Rasa Sindura and this lady scientist, and we decided to look at it through XAFs, extended X-ray absorption fine structure. It was done in Indore actually. The experiments are done in Indore. And XAFs doesn't give you the full structure, but tells you the coordination of the particular atom you are looking at, in this case mercury. What valency, what form that is there in that. And it turned out that none of that mercury, properly prepared, as you correctly said, properly prepared Rasasindura does not have any alpha mercury. And alpha mercury is toxic. And that is why. So, if you take elemental composition, it can be very misleading. This is what had happened when the British scientists looked at mercury is not in a chemical form which is toxic. I was doing a lecture on the Navati celebration of Dr. Arya Vaidishala. Navati is 90 years. So that his doctor was still very active at that time. And I said, I'll give you a counter example. Hydrogen is not toxic. I take the elemental composition of some compound. Carbon and nitrogen are not toxic, obviously body is full. So if you take the elemental composition of hydrogen cyanide, you will end up with the result that it is not toxic. So this is an example how, back to Sir C.V. Raman. This is Sir C.V. Raman, and he's holding a crystal of quartz with him. He was one of the original scientists in crystal physics. He looked at various examples of so happens that when I was a student in the Indian Institute of Science, by that time Raman had moved out to Raman Research Institute, and we used to go and listen to good lectures that were given there at that time. And he used to attend all of them. Lectures arranged in the Raman Research Institute. And come to my room, and you are welcome to come to my room. You will find 3 photographs behind my chair. These are the 3 of my heroes. C.V. Raman, the greatest experimental physicist India has produced. And in fact, that's the day we are celebrating. The whole 3 days, so this is the first beginning day. February 28th was the day he announced the discovery of the Raman effect. And one good habit we can learn from him is they always publish in Indian journals first. And then only he will publish abroad. Sometimes when you try to publish in journals abroad, the referee knows what you are doing, and you may lose priority when you publish it over there. He'll tell his friend that this guy is also publishing. I'll hold it back, I'll delay. Doesn't happen very often, but I'm just saying. But in the case of Raman, Homi Bhabha, the founder of our atomic energy program, thanks to whom we are all here, we are in so many aspects of nuclear energy, power, nuclear weapons. In fact, there is no field of societal or industrial activity, agriculture, medicine, in which nuclear is not present. It's kind of an omnipresent discipline. And the first day of the 98th test, Pokhran test, is celebrated as Technology Day. And Srinivasa Ramanujan's birthday is celebrated as Mathematics Day. Srinivasa Ramanujan, somebody wrote an article on him on his centenary, and he said, there are 2 kinds of geniuses. One kind of genius, when you hear about his work, you feel that if I had been a little more lucky, if I had been at the right place at the right time, I could have done that work. Call it ordinary genius. But there are people whose work, when you hear about, you ask yourself, how could any man have done it? and that is what he calls the magical genius. And he puts Srinivas Ramanujam in that category. No, I'll come back to Srinivas Ramanujam later when I talk of artificial intelligence. Yusuf has given me only half an hour. Already I've spent chattering about, okay. See, my title was Science Then and Science Now. Let me start with cost then and cost now. As Yusuf said, Raman made a Nobel. People think he spent only 300 rupees. So this man wrote an article a couple of years back, Rajendra Singh, that was not 300 rupees but 7,630. That's the figure you quoted, more or less. More or less you quoted that figure. But the rupee of those times. Just now Times of India, its centenary was over. And they published the first issue of Times of India. It was for 2 annas. Today I pay 7 rupees. So you see the difference. That is 56. Factor of more than 50. But even if you allow for that, the equipment Raman used was very simple. What was the cost of the discovery of the Higgs boson? And this guy, Alex Knapp, has estimated it very carefully. And that costed $13.25 billion. But then it's a little bit of an exaggeration. Comparison is a little extreme. So we need both kinds of basic research based on intuition. That's what led to Raman effect. Today, if he had wanted some money for studying the blue of the sky, which Raman was interested in, our funding agency will form a committee with Dr. Yusuf as the chairman of the committee, and they'll ask him a lot of questions like what is great about blue of the sky? It has always been blue, likely to be blue all the time. And by that time, he would have lost interest in it. But he studied with his own money, his own resources. And that is what led to the discovery of the Raman effect. So I have always said the highest intellects must be allowed to choose fundamental problems of their choice. Because you want money, the project has to be reviewed. But of course, today research costs are much higher because the need for advanced instrumentation. You are going to hear several talks about the synchrotron radiation source today. But then that kind of instrumentation is not used for one experiment. It is used for a very large number of experiments. And a lot of beamlines are used for protein crystallography, structure of biological molecules. You showed the picture of Venki Ramakrishnan, got the Nobel Prize studying the structure of the ribosome, for solving the structure of the ribosome. Most complicated structure ever solved by X-ray crystallography. Also, at least the possibility of design of new antibiotics. And most of his work was done using synchrotron radiation sources, the solving of that structure. And as a civilized world or country, we have to answer the fundamental questions like origin of the universe or the ultimate structure of matter, and the two mixed together in the discovery of the Higgs boson. That is the experiments with the Large Hadron Collider. See, when C.V. Raman announced the discovery of the Raman effect, Sommerfeld, who was a great scientist at that time, his student got a Nobel Prize. I'm not sure if Sommerfeld got a Nobel Prize. India had suddenly emerged in competitive research as an equal partner with her European and American sisters. That was a kind of a tipping point for Indian science, the discovery of Raman effect. And he himself writes in New Radiation, you see, the first case he was talking about primary radiation, because he was mostly using optical radiation. Today, as Yusuf showed, if you go to synchrotron radiation sources, other kinds of lasers, including X-ray lasers, you can cover an enormous region of the electromagnetic spectrum. At that time, first case, as he says, was fluorescence, scattering of light by atoms and molecules, and just scattering, as he says, gives us the light of this paper published in 1928 in the Indian Journal of Physics. Of course, his students, Krishnan and Ramanathan, both of them are great scientists in their own right. K.S. Krishnan and Ramanathan. Though they described it as feeble fluorescence, the impression left on my mind at that time was that we had an entirely new type of radiation. That's what Raman says in that paper. You know, this is something very interesting published in Vigyan Prasar. You know, when he went to get the Nobel Prize, he was sitting there, and when the Nobel, and you read it, it's beautifully prepared paragraph. When the Nobel Award was announced, I saw it as a personal triumph, an achievement for me and my collaborators. But when I sat in that crowded hall and I saw the sea of Western faces surrounding me, and I, the only Indian in my turban and closed coat, it dawned on me that I was really representing my people and my country. I felt truly humble when I received the prize from King Gustav. Then I turned around and saw the British Union Jack flag under which I had been sitting. It was then that I realized that my poor country, India, did not even have a flag of her own. And it was this that triggered off my complete breakdown. But Raman was a tough guy. And he broke down in tears. That's what the Vigyan Prasar Science quoting him. And today, you young people who are working in a free democratic India, you have huge opportunities. See, look at there's a beautiful biography of Chandrasekhar. Chandrasekhar got the Nobel Prize also. Speaking to his biographer, Kameshwar Wali. And Wali asked Chandrasekhar, how is it in those days India produced world-class scientists like C.V. Raman and S.N. Bose in the 1920s. And Chandrasekhar says, in the 20s, there was need for self-expression as a part of the national movement, to show the West that in their own realm of Western science, we were equal to them. That is at least the feeling of Chandrasekhar at that time. He was a great scientist. I'll come to that in a moment. I spent 3 weeks once because I was working with G.N. Ramchandran at one time on hydrogen bonding. And it so happened at that University of Chicago, Professor Chandrasekhar was there. But coming back to this slide, today, the motivation for young scientists should be to make India a developed country and a knowledge economy. See, Chandrasekhar, he was the first man who understood both the general theory of relativity and quantum mechanics. So when he combined the two in 1935, to define the critical mass called the Chandrasekhar's limit, above which the star would not become a white dwarf. That's called the Chandrasekhar limit. This idea, which later won Chandrasekhar the Nobel Prize, was immediately ridiculed by his guru, Eddington. Eddington understood, of course, he was a master in general theory of relativity, but he didn't understand quantum mechanics. So whenever Chandrasekhar spoke of his work, he ridiculed him. And in fact, because of Eddington, Chandrasekhar abandoned the field, which set the research back. All that related areas, black holes and all that, by perhaps 20 years. In fact, he was a very good Shishya, so he didn't want to attack. He left UK and went to Yerkes Observatory. Yerkes Observatory is very close to Chicago. So he got a job in Yerkes Observatory and he used to drive maybe a couple of hours, I don't remember. I think something like a couple of hours to the University of Chicago to give lectures. And he is the only known scientist, Dr. Vyas, whose entire class got the Nobel Prize. Only 2 students in the class only. Lee and Yang for non-conservation of parity. And they got the Nobel Prize before Chandrasekhar got his Nobel Prize. As I said, today we are wanting India to become a knowledge economy. The motivation is very different. Not just a developed country achieve the 17 sustainable development goals which United Nations has defined. That's the beginning. No poverty, no hunger, good health and all that. Beyond that, we want to become a knowledge-driven economy. A country, ability to develop new knowledge and the ability, of course, ability to use that knowledge and also use knowledge appropriated from other countries. This is what the already developed countries are doing. So we need a judicious mixture of basic research, applied research, technology development, R&D led innovation backed by high quality manufacturing skills. And all these must be in what I have called in one of my papers, I won't go into it, what I call coherent synergy. As I said, basic research is a cultural necessity in any civilized country. The highest intellects, I've mentioned it already, must be allowed. Then there is what I have called directed basic research. Not directed by anybody, directed by India's needs in the long term. India's societal needs, strategic needs, industry needs, but still basic research. It's not a substitute for self-directed basic research. Some people think I'm advising as though you replace that by it. I am not saying that. Self-directed basic research must be there. In addition to that, particularly in mission oriented, that's what we are doing actually. Something which relates to great Homi Bhabha. See, sometimes when there are leaders and the leader passes away, the system collapses. Particularly, the leader passes away prematurely. But Homi Bhabha created a leadership swarm around him. Because in TFR, you had people like M.G. Kimen and B.V. Srikantan and all that. And also new people he had hired. He used to start new programs around a person. Like Obaid Siddiqui in molecular biology, Govind Sarup in radio physics. And then, of course, within BAC, Homi Setna, chemical engineering, Raja Raman physics, Brahm Prakash metallurgy, A.S. Rao, electronics. And the culture he established here in the Department of Atomic Energy helped nucleate many more leaders in the next generation. You know, there's a very beautiful book by Arthur Koestler in which one of the articles he talks about 2 kinds of leaders, the yogi and the kamisa. The yogi is the contemplative thinker and the kamisa is the man of action. Most leaders are a mix, partly yogi, partly kamisa. But Homi Bhabha was a unique mixture of both, though mathematically absurd. Sometimes one feels he's 100% yogi and 100% kamisa. What are the things he got it done or planned before he passed away? He was also a person with great technology foresight. How many people can think of building nuclear reactors at a time indigenously? When at a time when we were not even building bicycles indigenously. And now we have grown. Even a few years back, when Yuki Amano was visiting Bach, and he mentioned that India is at the forefront of technological development in the nuclear sector. Of course, he was talking also about the nuclear fuel cycle, and the operators who are nuclear reactors are operating very well. I think at a time when you were saying industry has slowed down because of COVID, Kakrapar 3, the 700 megawatt PSWR, was synchronized with the grid on 10th January 2021. Safety and reliability go together, whether it's your personal car or a nuclear reactor. And look at the record. The Kaiga PSWR has broken the record, 941 days. And then, of course, they shut down for routine. Technology foresight, I mentioned. It's needed to select critical technologies for the development of a country. It's not the same as technology forecasting, technology foresight. And everything we know, nuclear, space, defense, strategic technologies, advanced manufacturing, nanotechnology, biotechnology, information technology, technologies related to MSMEs, related to rural development, and also thinking about these are all coming up, which are very important for India, various aspects of it. Cyber security, artificial intelligence, quantum computing, in all of which work is going on in BAC and I'm sure in other units of TAE. But you have to be careful. These are not static selections. That's why I like to give this example of President Roosevelt. President Roosevelt put together a team of engineers and scientists, leading ones, to tell him what will be the most important technology over the next 25 years. Look at the things they missed. Transistors, radar, rocketry, lasers, antibiotics, genetic engineering, and nuclear energy. Because the year after they submitted the report, Hahn and Meitner discovered nuclear fission. So when you do technology foresight analysis, which you must do, you can do it for the country, you can do it in any field, and that's what I don't want to go into. We know our foresight analysis showed we must close the nuclear fuel cycle, though some people not for entirely, whatever it is. And discovery of nuclear fission was basic research. It had nothing to do at that time about developing nuclear power. It came later. This is what I said when I talk about artificial intelligence. There are some people who are scared of artificial intelligence, including the great Stephen Hawking. Stephen Hawking has told a BBC correspondent, one day AI systems will take over the world. So you must control the developments in artificial intelligence. I don't agree with that. And then, of course, there are other people, Roger Penrose, the Penrose model in the quasi-crystal guys. I don't want to go into this. He applies the Gödel's incompleteness theorem to show that any cybernetic system or algorithm that you develop can never be smarter than the man who developed it, because it's your development. And this brings us to the idea of Srinivasa Ramanujan. As many of you might know, there is a book on The Man Who Knew Infinity. That was the book on the biography of Srinivasa Ramanujan, who died at 32. Like Adi Shankara, he died at 32. So he talks about it being a fascinating book. But I suggest a different perspective, namely the challenge posed by the mind of Srinivasa Ramanujan to the idea of super intelligent robots. He calls Ramanujan, I called him a magical genius from somebody else. He calls him a super genius. You all know, many of you know, most of you know Ramanujan's notebooks. Like our Shrutis, he never gave the proofs. He wrote the theorems. Either it was obvious to him or he thought it was not necessary. And still people are solving the theorems in his famous notebooks. And this fellow, this scientist, Professor Yehezkel Dror from the Hebrew University of Jerusalem, he writes that Ramanujan's theorems with novel ideas from his handwritten notebooks would, at intellectually back-breaking cost, be proved too, yet leave mathematicians baffled that anyone could divine them in the first place. This brings me to the current efforts to spawn robots. Now I'm talking of science now. I talked of science then, with artificial general intelligence behind them, beyond them, robots with super intelligence. And his conclusion is no enhancement of human intelligence opens a door to becoming a Ramanujan, and no algorithm is likely to produce robots with the abilities of Ramanujan. Of course, there is a book by Gardner on the different varieties of intelligence. I will not go into that. See, advanced technologies today are multidisciplinary. Designing of a nuclear power plant is not one technology, or synchrotron radiation sources or other particle accelerator. Department of Atomic Energy is a unique organization which has the capability, probably the only organization which has the capability to build accelerators or synchrotron radiation sources. Others can build, not that you can build missile launchers and other things, but facilities for science are, but these are all multidisciplinary. In fact, the disciplines themselves have become multidisciplinary. Theoretical physics, experimental physics, accelerator physics, and engineering. Where is the boundary between all these? The advanced ultra supercritical thermal plant, which had started in when I was the PSA. See, whatever you say, nuclear energy is renewable energy. Next 20, 30 years, you are going to burn coal. And if you make it more efficient, for the same amount of carbon dioxide produced, for the same amount of power produced, you reduce the amount of carbon dioxide that you produce. That's also relatively lower carbon technologies. Or, that involved organizations with multiple capabilities. IGCA, because the materials, they are the best in the country, and this is a materials problem. BHEL, the best designers of power engineering equipment, and NTPC, which are the best utility. If you want to do multidisciplinary, you have to create talent clusters. These are, of course, this slightly dated slide which Dr. Thakurta gave me when I was there. It's a very, very beautiful machine, 2.5. The Indus 2, by the way. Indus 1 is also there, which is for lower wavelength, lower energies. And of course, even then they were planning to build, which you saw on the slide, wigglers and undulators. I'm sure you will hear much more about it from scientists who are all, at least a couple of scientists. How many are from RRCAT here already in the audience? Quite. At least they are going to talk about it, maybe tomorrow. 3 undulators, they are going to talk about it. Of course, you can talk of Atmanirbharta. The world is becoming so connected that you must have international collaboration. And we are also willing to contribute. That's what, when this discovery of the Higgs boson I talked to you about, India had supplied, and RRCAT was the lead for that. The 1,800 or some number of superconducting character magnets, sextupole, octupole, decapole magnets, which had gone into it. So if you want to do such experiments, and of course in the case of ITER, International Thermonuclear Experimental Reactor, again, about the lead institution here is IPR, so BARC has also contributed quite a bit for that. And this cryostat in which that tokamak will be kept together, will be put together. This cryostat is being built by an Indian company, Larsen and Toubro, under the direction of the Institute of Plasma Research. And the base has already been established in May of last year. The base of this has been established. In fact, in my inaugural address a couple of years back, I was saying, fusion science is a physicist's delight and an engineer's nightmare. It's not an easy thing to do. See, want to become a technologically advanced country. There's no question about it. But we must remember that the foundation for a technology superstructure is basic research. There are many examples of this. I'll take this example of the Manhattan Project. Manhattan Project, plutonium is in fact, that engineer's nightmare, which I said, was first used on plutonium by the Los Alamos scientists. It's a very strange metal. If you cool it from the melt, at about 300 degrees, a little 200, 300 around about that, it solidifies, goes into the delta phase, which is 15 gram per cc. The solid to solid transition takes place as you go to room temperature, 19 gram per cc. So you solidify something at 15 gram and take it to 19 gram, it becomes porous and brittle. Obviously not usable in a weapon. All the people who are working on the Manhattan Project, they tried to solve the problem by pressing it and it didn't work. None of them worked. Finally, they went and asked Cyril Stanley Smith in metallurgy. He said, you add 3% gallium, it will never go to the alpha phase, problem solved. And he was not working on plutonium, he was working on all actinides. And he knew that by looking at the phase diagram that this is the solution. It's an example, and he was really a basic research scientist. My last slide. This is Peter Medava, Nobel laureate. Got the Nobel Prize for discovery of the acquired immunological response, physiology in medicine in 1960. Written a very nice book. It's there in our library. I picked it. At least it was there when I took it maybe 40 years back. I read the book, advice to a young scientist. And his advice, and always work on important problems. Important to science or important to society. How will you know it is an important problem? Well, that's your problem. You will have to find out. And in BRC, the young scientist, I've always used the term, and I use it here also. When I use the term scientist, I include engineers. Something like, as I said, there is no boundaries now. I got the award from the National Academy of Engineering. I told them, look, I'm not an engineer, but these scientists are working on basic research, applied research, technology development, and also providing high technology services. They're all working on important problems. So Medawar has given the advice to a young scientist. I think it is also good for not so young scientists. Not that old scientists can work on unimportant problems. They shouldn't do that. They should also work on important. I think let us remember, that's what all the great scientists, Raman, Bhabha, they all did that. And Let us remember this on Science Day. Thank you and Jai Hind.
Thank you very much, sir, for this enlightening talk and taking us to this exciting journey, which is really very inspirational to all of us. Dear students, with these blessings, we are now all set to start the technical sessions. But before starting that, we first show you some glimpses of Bhabha Atomic Research Center. For the next 10 to 15 minutes, we would be taking you to a virtual tour of few facilities of BARC.
Bhavatron 2, a technological marvel from Bhabha Atomic Research Center. Cancer, a dreaded malady afflicting millions of helpless victims, is caused by the uncontrolled growth of cells, leading to tumors and eventual organ failures. Radiotherapy provides the means for selectively killing the cancerous cells with minimal damage to the surrounding healthy tissues and organs. The suspected tumor is exposed to high-energy radiation beam from an external radiation source emanating gamma radiation or by a linear accelerator providing high-energy X-rays. Bhabha Atomic Research Center has developed an indigenous cobalt teletherapy machine, Bhavatron, which has changed the paradigm of cancer treatment in India, transforming a high-cost treatment procedure provided by expensive imported machines with limited availability to a low-cost and affordable treatment method widely available across the country. Radiation source in Bhavatron is a cobalt-60 source of up to 15,000 curies obtained from Indian power reactors. Bhavatron 2 is a state-of-the-art teletherapy machine with several advanced features for precise and safe operations. The systems are automated for computerized control over the treatment and operational procedures. Cobalt-60 radioisotope in the form of a sealed capsule is remotely moved from a shielded chamber to the treatment position to expose the target volume for a predetermined duration. Patient data is stored for quick retrieval and precise patient positioning on the treatment couch. Immobilization devices ensure accurate and reproducible patient positioning. Motorized wedge filter for any desired gradient in the dose profile. Low power consumption facilitating battery backup for regular operations even during power outages. Enhanced safety ensured by automatic and full collimator closure during any unforeseen eventuality. To improve treatment outcomes, it is imperative to incorporate systems for dose conformity to irregular tumor boundaries and variety of shapes and sizes. A multi-leaf collimator serves this purpose and has been incorporated into a cobalt teletherapy machine for the first time in Bhavatron, located at Advanced Center for Treatment, Research and Education in Cancer, Navi Mumbai. The MLC system comprises 60 tungsten leaves which can be adjusted to create the desired shape and size, as advised by the radio-oncologist. The process of setting leaf positions is automated and performed by a dedicated software developed for this purpose. Additional features to enhance the system are being continuously developed and incorporated for improved outcomes. The equipment is compliant
to national as well as international standards and has received wide acceptance by the oncologists. It has been installed at over 60 centers in the country and several abroad as well. The technology has been transferred to medical equipment manufacturers for commercialization. The superior quality, economical cost, simpler machinery and lower maintenance regimen of Bhabatron 2 is expected to result in wider spread of teletherapy treatment across the country. Since more hospitals and clinics would be in a position to purchase and operate these units, it can be considered a significant milestone in the peaceful uses of nuclear energy and the Atoms for Peace agenda of the nation. For further details, please contact Technology Transfer and Collaboration Division, VARC.
India, a country with a diverse climate, has over 100 crores of the population to feed. With the advent of the green revolution, the Indian farming scenario has changed positively. But due to poor post-harvest techniques, a huge amount of food is getting wasted. We need to preserve food after harvesting to prevent food wastage. In India, we have been preserving food by heat processing, dehydration, the addition of chemical preservatives and other methods. Some vitamins and other micronutrients are sensitive to heat that degrade during heat processing and storage. A better post-harvest technique to ensure safety and quality of the food is the need of time. Food irradiation is one such technology that can ensure food safety while retaining its nutrition and freshness. We are all aware of the electromagnetic spectrum, which includes sunlight, microwaves, radio and mobile signal, X-rays and gamma rays. Among them, high energy rays such as gamma and X-rays can pass through the food and kill the harmful bacteria and insects. These high energy gamma rays are emitted by isotopes of cobalt and cesium. High energy rays also can be generated by machines such as X-rays and electron beam. These high energy rays are used to process food, which makes it safe for consumption. The cobalt-60 used for generation of gamma rays is stored inside water when not in use. During radiation processing, the source is lifted from the water shield. The food to be irradiated is packed and filled in product boxes and placed on the conveyor belt. The product boxes move around the cobalt-60 source. The speed of the conveyor belt and the exposure time can be changed depending on the dose that is to be delivered to the food. During irradiation, the food will never come in contact with the radiation source and only high energy beam passes through food. Radiation processing is a useful application for the various purpose. A low dose of gamma rays could be sufficient to delay the ripening of mango for long distance transportation. Previously, Indian mangoes were not exported to the USA due to the presence of seed weevil. Radiation processing has ensured insect-free mango and thus has enabled us to ship mango to the USA. More than 8,000 metric ton of mango has been exported to the USA and the quantity is increasing every year. Now more fruits like pomegranate are being irradiated. Gamma rays also prevent sprouting of onions and potatoes. Disinfect cereals or pulses by killing microscopic insect eggs. Gamma rays can effectively eliminate spoilage microorganisms and kill disease-causing microbes in spices, fish, meat and minimally processed vegetables. Similarly,
Shelf-stable food can be prepared by using the higher dose of radiation. Astronauts carry irradiate food, which is totally safe for eating. Radiation processing is a cost-effective technology. More than 50 years of research has been done on radiation processing of food. International agencies like Codex, WHO, FAO and others have accepted radiation processing of food as a safe food processing technology. In India, FSSAI has approved radiation processing technology and has set the dose range for various food commodities. Food Technology Division of Bhabha Atomic Research Center is focused on cutting-edge research and development activities. It aims to provide modern food processing technologies that would aid farmers and consumers. These technologies would address current food safety and security problems. Some of the technologies developed are shelf-stable products like pulao, puran puli, stuffed bag products, meat and fish products. These products can be kept at room temperature and have an extended shelf life. Radiation processed health drinks and energy-rich fluids for immunocompromised patients. User-friendly technology to preserve delicate foods such as lychees. Biodegradable packaging material to reduce the use of plastic and many more. To promote awareness and uses of this technology, Department of Atomic Energy has set up 2 technology demonstration units at Navi Mumbai and Lasalgaon. The technology has been successfully adapted commercially. 2 plants by state governments and 11 by private entrepreneurs, and many more are coming up across the country. Food irradiation technology is beneficial for enhancing shelf life and safety of food, promoting domestic and international trade, retaining nutrition value of processed food, and development of biodegradable food packaging. Radiation processing is the technology that can certainly ensure food safety and security for the present and the future generation.
Radiation and Isotope Technology, or BRIT as it is commonly known, is a wing of DAE dealing with the production and marketing of radiation sources and radiopharmaceuticals for various applications. BRIT supplies cobalt-60 gamma source used in Bhabatron, sludge hygienization plants, food irradiation facilities and mutation breeding experiments. The other most important mandate of BRIT is the supply of radiopharmaceuticals for diagnostic and therapeutic purposes, which are manufactured in state-of-the-art facilities using remote operations. Iodine 131 capsules for diagnosis and treatment of thyroid-related disorders is an important product. The manufacturing process involves the filling of capsules with the anhydrous powder and transferring them to a shielded hot cell for the remote addition of iodine 131 solution. After measuring the activity dispensed, the capsules are transferred to shielded lead pots, sealed, labeled and packed for transport. BRIT also manufactures technetium-99m based radiopharmaceuticals in clean laboratories in the form of cold kits, using sterile equipments and containers to eliminate microbial contamination. The final product is delivered in the form of freeze-dried powder. The technetium-99m generator, manufactured by BRIT, is a device containing alumina columns loaded with the parent product molybdenum-99. Technetium-99m, which is the daughter product, is then milked from these columns by the end user using saline solution. The extracted technetium-99m is then incorporated into the radiopharmaceutical. BRIT also supplies radioimmunoassay kits to diagnostic centers all over India. These RIA kits containing the labeled and unlabeled antigens as well as the antigen-specific antibodies are manufactured in an ISO certified laboratory of BRIT. The manufacturing procedures at BRIT are subjected to rigorous quality control protocols using state-of-the-art equipments to ensure the purity and sterility of radiopharmaceuticals. BRIT plays a vital role in the use of nuclear medicine and radiation therapy procedures for disease diagnosis and therapy and is regarded as an important contributor to the health security agenda of the nation.
Dear students, we will now show you a movie on synchrotron radiation emitted by electrons in large-scale facilities, which will set the tone for the upcoming talk by Professor D.D. Sarma, who will be joining us from Bengaluru after this 5-minute movie.
The world around us is made up of matter, which is composed of atoms that cannot be seen by the human eye. To see atoms, X-rays, which have much smaller wavelengths than visible light, are needed. Other invisible radiations like ultraviolet and infrared rays are useful for studying vibrations of atoms in molecules. Laboratory-based experiments to probe atomic scale phenomena are often limited by lack of sufficiently bright and tunable sources of these radiations. The synchrotron radiation source, which is one of the marvels of modern science, produces highly intense radiation spanning the entire range of visible as well as invisible wavelengths. What is synchrotron radiation? When any charged particle like an electron is accelerated along a circular path by the action of a magnetic field, it emits what is known as dipole radiation. When the speed is increased till it is close to the speed of light, an extremely bright and well-directed radiation is emitted. The machines used to accelerate electrons to such high speeds are called synchrotrons, and the emitted light, which contains all wavelengths from infrared to X-rays, is called synchrotron radiation. In a synchrotron radiation facility, electrons emitted by an electron gun are first accelerated in a microtron or linear accelerator, after which they enter a circular accelerator called a booster synchrotron. Here, the energy of the electron is boosted up to high speeds, approaching the speed of light. Next, the electrons are injected into a storage ring made up of alternate straight sections and curved sections, consisting of different types of magnet arrangements. In the storage ring, they circulate at a constant speed for several hours or even days. The emitted radiation is used for different types of experiments. Over 50 light sources are in operation all over the world, including the Indian synchrotron radiation sources Indus 1 and Indus 2 at the Raja Ramanna Center for Advanced Technology at Indore. Scientists from physics group of Bhabha Atomic Research Center have set up several experimental facilities at Indus 1 and Indus 2. The fundamental parameters used to probe the physical world have given rise to various experimental techniques. For example, in photoelectron spectroscopy, X-ray photons knock out electrons from the sample. By measuring the energies of these electrons, valuable information is obtained about the energy levels of the atoms in the sample. In X-ray diffraction, incident X-rays are scattered from the sample and interfere with one another to form a diffraction pattern. By analyzing this pattern, scientists can reconstruct the structural arrangement of atoms within the material. Today, synchrotron radiation is widely used for scientific research in diverse fields. A number of groundbreaking discoveries were rendered possible only with the advent of synchrotron radiation. Several Nobel Prizes have been awarded in the area of synchrotron science and technology. Recently, the structure and interactions of proteins linked to COVID-19 have been solved using synchrotron radiation. Truly, the use of synchrotron radiation as a light source has revolutionized modern scientific research.
Dear students, we now present to you one of the pioneers in this field of science, Professor D.D. Sarma from Indian Institute of Sciences, Bengaluru. Professor Sarma is the fellow of all three science academies of India as well as the World Academy of Sciences, with several publications, patents, awards, and academic positions to his credit. I now request Professor Sarma to deliver his talk, who has joined live from Bengaluru.
Thank you very much. Thanks a lot for giving me this opportunity to be joining my young friends. I wish I had a chance to join them in person and shall look forward to such an opportunity in the future, because it's a totally different thing to be interacting with all of you, the young budding scientists of the future. The world depends on you, and I would love to see you in the next round, next installment of this, when we would have this pandemic behind us. This is to the organizers, I still don't have the share permission. Can you give me the sharing permission, please? Okay, thank you. It's come. Now let me share my screen and give me a moment. And let us make sure. Can you see my screen? I guess you can, right? Okay, and I'm trying to see if I can get, yes, thank you. I see the thumbs up. I'm trying to now see if I can get the laser pointers in some way. Give me a moment because I'm not entirely familiar with this one. Okay, I don't see the laser pointer. Normally it should show up here, but it doesn't. So I hope you can see my cursor at least. So what I'll be talking about today is the basics of synchrotron radiation and its utilization. Some part of it would actually overlap a little bit with what you just now saw in the beautiful movie. I'll show you some bit of that too, and I'm sure repetition is not going to hurt you. It will help you to remember things. So I'll start by telling you what basics of synchrotron radiation, the basic units, basic structure, basic science at a very elementary level, so that I do not require your knowledge base more than what you have studied in your school, because I'm sure most of you are from the senior level of your school and junior level of your college. And I'll also try to give you a feel for the range of applications in various scientific studies that synchrotron radiation is used. Actually, synchrotron radiation is used for almost every application, every science and technologies and engineering sciences. It's so much used and so varied that it's impossible to give you a complete flavor of it. In fact, it's used also in studying archaeological objects, not only in sciences. So it has a footprint that is really huge. But before I start off talking about synchrotron radiation, let me think of a circular track. What I have drawn over here is a circular track, and consider that there's a particle rotating with a constant angular velocity omega. All of you know that that is an accelerating particle. There's a centripetal force mv squared over r. And so this, though it has a constant speed, this particle with a constant speed rotating around is actually accelerating. That force is given by this centripetal force. Now I can, instead of having this kind of an object where I have this particle, a massive one, I can think of it being an electron. How can I make an electron move in circle? That is also actually possible. If you put an electron in an uniform magnetic field, you know that an electron in a uniform magnetic field experiences a force which is V cross B, V being this velocity of the electron, instantaneous velocity of the electron, and B is the magnetic field. Now, think of this plane in which the electron is moving, and it has a constant velocity in this direction at this point of time here, and all the magnetic fields are pointing out of the paper. That is shown by these crosses. So at this point, there's a V cross B force on the electron, which is in this direction. And that will immediately bend the electron. And if I can make this E V cross B term such that it provides exactly the centripetal force required to make this electron move with a speed of V in a circle of R, that means if I set mv squared over R to be equal to E V cross B, then you can see this electron will go round and round in this orbit forever. But it actually will not go in orbit forever because of a very important thing. There's a very important property of all charged particles, not only electrons, that any accelerating charged particle, and as soon as it has a constant speed, but since it's rotating, it has an acceleration. So that accelerating charged particle, in this case electron, will emit electromagnetic waves. As soon as it emits electromagnetic wave, that means it will actually lose energy. And as it loses energy, it will become, the velocity will become smaller, the circle will become smaller, and it will try to fall down. In fact, this was exactly the puzzle that made Niels Bohr postulate the initial version of the quantum mechanics that said that electrons in an atomic orbit cannot continuously lose electron, because if it did, then Bohr argued that it would have fallen into the nucleus. But in this case, that is not the case. In this case, as soon as it emits the electromagnetic wave, it will lose its energy. So in order to keep it going always in the same orbit, the energy that it loses, I must feed back that energy into the electron in some way, and that is done by RF frequencies coupling to the electron and giving it the energy that it requires, so that it keeps rotating in circle forever, and always giving out these electromagnetic waves that we call the synchrotron radiation, and these radiations come out tangentially in the direction of the instantaneous direction of the speed of the system. Now, that is synchrotron radiation. Then whenever it's bending, it's going to come out this way. Okay. Good. I have the possibility now. Let me see what is coming up. Allow annotation. No. Okay. All right. Okay. So these synchrotron radiation will be coming out. They are continuum electromagnetic waves, and I can make use of them to do any experiment that I want. So what do I need to achieve this? What happened? Wait a minute. Okay. So how does the whole thing work? You have already seen the movie. In the movie, what was shown, that electrons will be generated at this point, and then they're accelerated in a linear accelerator by applying voltages to a very high energy, and then they're injected into this stage, which is called the booster stage. So it's accelerated up to this point, and they are injected in here, which is called the booster, and that accelerates the electron by giving it more and more energy and bring it up to very close to the speed of the light. And at that energy, when the energy is the required energy that I need, it's pumped into this electron, ring, what we call the storage ring, and here it goes round and round, and whenever it bends, it gives out this electromagnetic wave that you're seeing. And then there are laboratories that we set up at the end of this, which make use of this electromagnetic wave coming out to do whatever kind of science that you want to do. So that is a basic unit it does. How do I make it bend? As I have said, that if you apply electromagnetic field, the electron going in straight line will deflect and bend. As soon as it bends, that amounts to actually accelerating the electron. And so this green cone that you're seeing is light that is coming out because it is bending. It is not only this bending stage that you can get out electromagnetic wave. These days, for technical reason and for great benefit of synchrotron radiation, there are other techniques by which we can get the light up. What do we do? When the electron is going even in straight path, not in these bending magnets, but going in straight path, we put magnets with their poles opposite, north, south, south, north, north, south, south, north, like that. So that what the electron does, it begins to bend in one direction and immediately it feels that the polarity has changed and it bends in another direction. So this bending keeps getting reversed and then it doesn't bend out of the path, but it jiggles around the straight line path. And this jiggling around is also an acceleration, and so it gives out beautiful light, very intense light along the average straight path of the electron that can be used. And if this jiggling around that I talked about is done in a manner such that it has a coherence with the motion of the electron itself, then this electromagnetic wave that was coming out interacts with the electron itself and therefore becomes even better quality in terms of intensity and becomes much more focused, and then it comes out. This technique is called putting a wiggler, and this is done on the straight path of the electron. There's an undulator also on a straight path, and the bending magnet on the bending stages of the synchrotron ring. So this is how the light is created. This is a very short movie, exactly of the sort that you have seen. Electron is created somewhere here, and then it's accelerated, injected into the ring, and then what happens is, these are the bending magnets. That's where the electron bends and gives out radiation, which are taken down this way. You can also, in the straight path of the electron, put those alternating poles and jiggle the electron as it is going, and that will give out electromagnetic wave. You can take it out straight and then split it into different parts, take it out and do experiments, and these are the bending magnets. So watch what it does. It will be first producing the electrons in the electron source. Those electrons will be accelerated. This is the electron source that you're seeing. It produces electrons accelerated, they're injected into the ring. And as they're injected into the ring, this is the bending magnet stage here that gives out electrons bending. And then there is straight line path where also I can make them jiggle. This is actually where I feed in the energy again, the energy that the electron loses, so that it stays in the orbit all the time. And at the bending stages, it will start to give out electromagnetic waves. In the straight segment also, it gives out electromagnetic waves. These electromagnetic waves are very broad spectrum, and these broad spectrums are taken down through these pipes that are called beam lines. And this beam is wide electromagnetic spectrum that is then monochromatized, and you take out the frequency that you need or the wavelength and do some experiment, whatever experiment you desire to do. I'll talk about those experiments in a moment. But that was a schematic and looked very simple, but it's actually very complex. The bending magnet that I'm talking about is a huge object that can weigh several tons, as shown over here. As you can see, the inside is not as simple as I showed you in the schematic. You can see people standing here, and this is where the electrons are bending and they're assembling the thing together. You can see two people sitting up there. There's a big wall that is created to shield radiation, because huge amount of very high intensity X-rays, gamma rays, and all kind of rays are being produced. And if all of it came out, people trying to do experiment outside will all get afflicted and very dangerous by this dangerous electromagnetic wave. So you have thick cement wall, concrete wall that stops this electromagnetic radiation. These are the people who are creating that wall around, and all experiments will be done outside. Through a small hole in these walls, the electromagnetic wave is taken out for the purpose of doing experiments. What is the typical size? Typical size of a synchrotron source can vary. These are the smallest ones. There's a Helios Oxford instrument, Helios instrument. You can see there is an individual standing. And so you can see that it's not a very large size instrument. And then you can have another called Spring 8. And this is the synchrotron radiation center. And this is the hill inside the center. So the entire ring is built around the hill. So you can imagine how big it is. It is a couple of kilometers in circumference. So it's a huge object. So from very small to very large, depending on what kind of experiment you want to do, you have these things. What is the kind of intensity of light that it can give? Well, to give you an idea, a candle gives out per second number of photons that it gives out is about 10 to the power 5 in some unit, some solid angle, a small solid angle. In the same solid angle, a 60-watt bulb will give you 10 to the power 6 photons. X-ray tubes give you between 10 to the power 8 and 10 to the power 10 photons. Sun in such solid angle gives you about 10 to the power 10 photons. The bending magnet gives you 10 to the power 15, and those undulators, the ones that wiggle the electron, can give you 10 to the power 19 photons per second in that solid angle, which implies, compared to the sun, you have a 1 billion times increase in the intensity, 10 to the power 10 to 10 to the power 19. I don't know how many of you know that famous statement from Oppenheimer when he saw the first nuclear blast and saw this fantastic power of atomic energy. He had very famously quoted a shloka from Vedas saying, which translated into brighter than 1,000 suns. And what we are seeing here is brighter than 1 billion suns, because it's 10 to the power 9 times brighter than the sun. And that tells you the kind of energy that you are working with, the kind of high energy photons that you can get, and the intensity of photons that you can get. Now, I talked about the intensity. Let me talk about the energy that I was mentioning. The electromagnetic spectrum is actually an extraordinarily broad spectrum that in terms of the wavelength shown over here ranges from more than 1 kilometer, that's called long wave, radio wave in the order of 1 meter, goes through radar, microwave, infrared. The visible range is a very small range. Then ultraviolet, X-rays, gamma rays, cosmic rays, 10 to the power minus 12. So you can imagine the range that it is covering is almost 10 to the power 15 orders of magnitude in wavelength. Now, the way this part is used, so you keep this in mind, and I'll show you what synchrotron can give me out of this fantastically wide spectrum. It can give us, of course, this, every now and then I get stuck. Yeah, so this particular part, the one that you're familiar with, the beautiful colors, is actually a very narrow range of frequency and wavelength. Here I have given you the electron volt, the energy of the electromagnetic spectrum, and corresponding wavelength. I was telling you about wavelength cosmic rays of 10 to the power minus 12 meters, long wave in terms of 10 meters. An object, to give you an idea, truck is in the long wavelength region, a cricket ball, which is in the order of a bit less than 1 meter, but more in that 1/10 of a meter, and is in the millimeter size, if tens of millimeter, 1 centimeter size, virus, and then macromolecules down to crystals, atoms, inside of atoms. So electromagnetic wave and this wavelength, if they're comparable, then I can study these objects. And synchrotron can give you this range of wavelengths. That is from somewhere up to here to down to somewhere up to here. From, in terms of energies, to hundreds of kilo electron volts to sub-milli electron volt range. So there's a fantastic energy range and fantastic wavelength range with which I can study macroscopic objects, microscopic objects. Processes that require very small energies, processes that require very high energies. The energy and the brightness of the photon, the intensity and the brightness of photons that I talked about, is actually going up exponentially with these synchrotrons coming in. This is the old technology, 1900, a little before, Röntgen discovered X-ray tubes, production of X-rays. And the brightness was in the order of 10 to the power 7 photons in that unit of solid angle. rotating anode push it up, and that took us 60 odd years. And now we're going up farther, and very rapidly you can see how we are getting more and more photons in a very short time in the development of synchrotron radiation. And the way the photon intensity is going up, I have told you, this is the energy of the electromagnetic spectrum that I can cover, and this is the photon intensity that I can cover, or number of photons per second within the unit of solid angle. Bending magnet gives me wide spectrum, continuum, and fairly intense. Wiggler gives me even more intensity, brightness, and wider spectrum. And undulators give me narrower spectrum, but I can have different undulators to achieve super bright sources, giving me huge number of photons that I talked about as billion times brighter than the sun. There are additional properties that are very useful of synchrotron. It comes out very tightly focused. I talked about it and showed you. It comes in a very tightly focused, and so all the intensity is bunched together already, and I can bunch it down further to less than a micron size, and so I can do very well imaging. I can image with it. It also happens to be highly polarized source, and that has great advantages in many, many techniques that are used. And also, since the electron, you saw they're bunched, so it was electromagnetic wave. In wavelength is continuous coming out, but in time, these are pulses that are coming. I get one pulse, then another pulse, and typically this pulse is, the width is in the order of nanosecond or even smaller I can make. That means it has a time structure, and because it's a pulse, you know stroboscope. Have you seen? Okay, I cannot ask you because we are not together. A stroboscope is a flash of light that has a time structure, and you can actually measure how, when something is rotating very fast. If you look at it with a continuous light, then you will find you will not know that it is rotating. But if you now flash the light, and flashing light lights it exactly once for every rotation, then of course you will see static, because every time light flashes, the object is in the same orientation. And this is something that, in fact, you can experience if you look at the tube light at home and move your hand in front of it like this, looking through it, you'll see that your hand is not moving continuously, but moving in a staggered, structured manner, simply because the tube light, because of the frequency of the power that we get in our home, is switching on and off. So it's like a stroboscopic light, and therefore it lights up your hand only in a certain frequency, and that gives you that structure. So we can use this particular structure of light to this kind of stroboscopic experiments also with synchrotron radiation. Now, so what is a synchrotron radiation? Let us summarize before looking at the kind of applications that you can have in the next 10 minutes that I have. A continuum spectrum of electromagnetic wave, I've told you. It covers a very wide energy and wavelength range. Of course, these two are related. It has extraordinarily high intensity. It's highly polarized, and it's very, very focused. And it has a time structure, and it is coherent. It is a very powerful tool for investigating almost anything, because it has such wide energy and wavelength available to it that it can study almost anything. It can see very small things with better contrast and detail. It can see things happening faster because of this time structure. It can make very sensitive measurement because it's very high intensity and because it's polarized. Wow. Is somebody drawing these things, or I am drawing it on the screen? There's some structures that are coming up on the screen that I am not doing, and it seems to be done by somebody else, but maybe I'm doing that. I don't know. Anyway, these are very large multi-user facilities. At any time, there are many, many people that are working on this facility at a time, and it works 24 hours a day. It's not something that is working only once in a while. It's really very disturbing to have this annotation request continuously coming up on my screen. If I don't approve, I hope that somebody is taking care of it, because when I approve, I get these lines coming on my screen. And that's really causing me disturbance. Anyway, let me continue. So, and it covers practically all areas of science. Now, I'll give you some examples. this approve. I don't know if you see, and I keep getting this approve request constantly. So it can cover atomic science, solid state, radiometry, semiconductor physics, microelectronics. I talked about archaeology, archaeometry, material science, biology, tomography. Every variety of areas can be covered. I'll give you a few examples right now. There is this constant marks. I don't know how they have come. I have not put them, and I don't know how to get rid of them. So I will leave them there. Typically, what is happening is there's an electron source that's going in orbit that gives me X-ray, to make things very simple. And this, I put some optics to make this X-ray even more tightly bunched. I take it to sample, it interacts with the sample, and I have a detector that detects what happens to the radiation after it has interacted with the sample. With that, I can do different kinds of techniques, and techniques are given here. I can do spectroscopy, I can do scattering, I can do imaging, I can do dynamics at the time. I'll take brief example from each of these categories to give you a feel for the kind of things that can be done. Not every type, that is not possible, and you'll also find it too heavy. Let me give you some simple examples. In talking about spectroscopy, let me talk about the spectroscopy. Maybe you know about photoelectric effect. Albert Einstein got his Nobel Prize because of photoelectric effect. Where what you do is think of a material which has a lot of electrons, and these electrons are in energy levels. These are the core levels, electrons sitting there. I come in with some photons with fixed photon energy. They knock this electron out. The electron absorbs this energy and gets excited and comes out and becomes free electron. I can measure the kinetic energy of this electron outside. I know the photon energy. The difference between the two is the binding energy of the electron. And the binding energy, so there is a simple energy conservation rule that says photon energy must be equal to the binding energy I need to overcome plus the kinetic energy that I measure, right? So these I measure, this I know, and so I can evaluate the binding energy. And it turns out that the binding energy of an electron is absolutely characteristic of the element. So by knowing the binding energy, by measuring the binding energy, I know what element is there in the material. So it is very powerful tool to find out what is elements that are present. In fact, that's why it's also called ESCA, because it's element sensitive, element specific chemical analysis. It does electron spectroscopy for chemical analysis. And this is the reason long time back, Ty Sigburn got the Nobel Prize for discovering this technique. And that can be using X-rays because I need a lot of energy. The energy of X-rays typically in hundreds and thousands of electron volts. And I can pull out the core electrons and find out the elements. And by finding out the elements, what I can do, imagine a nanoparticle, a very small nanoparticle that I've made, which has a cadmium selenide inside and cadmium sulfide outside. We call it a core shell structure. A nanoparticle, a very small nanoparticle that I've made, which has a cadmium selenide inside and cadmium sulfide outside. We call it a core shell structure. And then what I can do is to map out the elements that are in the core. I see there's cadmium and selenium. And I map out the elements that are outside. I find that instead of selenium, I have sulfur. And so I know exactly the structure of this nanomaterial. This whole nanomaterial may be only 5 nanometers, 50 angstrom across. And yet, by doing the chemical analysis of elements, I can figure out how the structure is. Or I can say, no, look, selenium and sulfur have got mixed together because I find some selenium and sulfur content and that continuously changes. So I can figure out the internal structure of nanomaterials by doing an elemental analysis using those photoelectron spectroscopy. Photoelectron spectroscopy can also be done with lower energy UV radiation as well as UV radiation. With a visible, we can do some other electronic excitation. Typical energies that we are talking about is between 1 electron volt and 100 electron volt. With that, we can do this kind of very careful study that are very sensitive to not only the element, but also what chemical state the element is in. What kind of band gap it has. If it is a semiconductor or insulator, I can measure the band gap using this. I can also find out what is the excitonic binding energy, and all this very important understanding of the property of material I can extract by doing photoelectron spectroscopy with UV radiation. With IR radiation, I cannot pull out electron because the energy is very low. The typical energy I'm talking about is in the order of 1 milli-electron volt to about 1 electron volt. Energy range in which the vibration of the molecules or solid where the atoms are vibrating, the typical vibrational frequency, the energy corresponds to this. That means that if I shine this energy coming from synchrotron into a material, I can excite these vibrations and my photon will be absorbed. So by measuring how many photons are getting absorbed, I can figure out how the molecules are vibrating inside the material using this energy range. By using even broader energy range in a microwave, we can figure out the rotation of molecules because they need very low energy, and I can excite the rotational energies of the molecules and other systems to figure out. So you see that when I have such a wide range of energies available to me, I can do all these experiments of spectroscopy using different energies to excite different processes in the material. I talked about imaging. Let me talk about imaging. And this is the kind of image that you know of. This is what Röntgen used the X-rays first. It is called the intensity contrast. You allow photons to go through. This is actually a finger of a dead body, and looking at the finger, and the bones don't allow the X-rays to go through, so it becomes dark. The flesh allows the photons to go through, so it's light, and you can see it. But you can't do much more than that. But X-rays or whatever the electromagnetic wave that you're sending not only has intensity, which changes while going through bone or flesh, and that's the contrast you're picking out, the intensity contrast. A wave also has a phase, and if you do a phase contrast imaging, then you can get details of this kind. And this is what you can do with the synchrotron radiation. And you can figure out both. You can go from here to here by doing phase contrast imaging. Look at the beautiful way that the kind of imaging that you can do of a fly here. The fly can be imaged, and you can image by phase contrast. You can look at inside, you can magnify only the head part, the eye part, look inside of it, depending on which wavelength you use, whether you are making it elemental sensitive or not. And all these details can be extracted by doing synchrotron radiation imaging. Not only that, for example, old paintings, and this is in fact being used in Italy extensively, how these great masters, Leonardo da Vinci, made his paintings. It turns out that you can analyze the painting layer by layer. We see only the top layer like this, but using synchrotron, you can look at the layer below. And sometimes you see how the painter changed his painting over the years, putting more and more painting on top, and evolved his painting from earlier to later period. And that all can be mapped out. And in fact, this becomes very important if you preserve these very old paintings. You need to understand what exactly were the paints that are being used and the layers of it that have been used. You can combine spectroscopy with imaging, because imaging comes from the fact that I have tightly bunched my photon. But use this tightly bunched photon, I can be element specific. And if I'm element specific, I can identify the element by doing spectroscopy, and I can imaging because I have the space resolution. And here is an example where a material that was being made with lanthanum strontium manganate and lutetium strontium manganate, you can see only lanthanum and lutetium are different. And when they're mixed together, one hoped that they'll mix, but what happened is that they beautifully phase separated, creating a pattern inside the material. And this each width is about a micron wide, and you can see the white part is lutetium strontium manganate and the black part is lanthanum strontium manganate. That's because we are doing an element specific mapping. I'm asking where is the lutetium and where is the lanthanum. Spectroscopy can do that, and I can get it space resolved because I have made the photon very tightly bunched. That brings me to the question of how small then can I see? And this is where the wavelength that we are talking about comes into play. Now, different objects have different lengths. Like human hair is in the order of hundreds of microns. Human cells, integrated circuit that you use inside the integrated circuit, the structures down to now 10 nanometers, biological macromolecules, and atoms and molecules are 1 nanometer and bigger. Now, wavelength of the synchrotron can range, as you know, down from very small to very high. So there are many internal probing that I can do of these using synchrotron. More than that, I can even bunch my synchrotron radiation these days better than 100 nanometer. So I can do imaging down to this level of wavelength, and any object of that size can be imaged now using synchrotron radiation. And this is the last set of examples I'll give you when I'll talk about diffraction. Hopefully you know about diffraction. This is nothing but interference. If you have a plane of atoms, another plane of atoms, this first plane of atom, the electromagnetic waves gets reflected like this. The second plane of atom also reflects the wave, and you can see that the path difference between these two is 2d sine theta when the layer separation is d. This is just a geometric construction. And that tells that these two waves will interfere with each other when 2d sine theta is an integral multiple of the wavelength. This is the interference pattern that you know when you put oil and water, you get this thin film of oil that gives out beautiful rainbow color. That comes from interference. Here, the interference happens for so many layers of these atomic layers that it gives us a diffraction, very sharp interference pattern. And the equation that I just now said, any integral multiple of the wavelength, when it is equal to the path difference, you have a diffraction peak. Looking at the diffraction peaks, and the peaks are shown over here for objects, you can find out how the atoms are distributed in simple materials, as shown over here. These are each atom constructed from this diffraction. Or fairly complicated atom structure can be also solved. Not only that, big protein molecules, and this was also mentioned in the previous movie. This is the coronavirus. The protein structure has been solved. This is the spike protein of the coronavirus, whose also protein structure has been solved by doing diffraction technique using synchrotron. And these are the last two examples that I wanted to show you to give you a flavor of what can be done. And I'll stop with leaving a little bit of time for discussion if you'd like. Let me end by thanking you and the organizers for giving me this opportunity. Thank you very much.
Thank you very much, Professor Sharma, for this scintillating talk. You can now stop sharing the screen.
Yes.
We have a short time for a few questions. Students who wish to ask any question can raise their hand on WebEx. Students who wish to ask any question can raise their hand on WebEx. I understand it is difficult in online platforms, but still if we are able to take a few questions, that would be very nice.
Dear students, after this Professor D.D. Sharma's excellent presentation, he is ready for answering your questions and doubts. Please come forward.
Mr. Adarsh,
normally, yeah, sure. Go ahead. Normally, I threaten the students. If they don't ask me a question, I'll ask them questions. And that's when they start to ask questions quickly.
Sir, Mr. Adarsh George Matthew wants to ask you a question.
Sure.
Mr. Adarsh George Matthew, you can please unmute yourself and ask your question.
Sir, actually, I wanted to ask whether it will be able to solve the challenges that are faced today, such as I wanted to ask 4 questions. Like, is it in any way linked to the National Hydrogen Mission?
Yes, it is. See, the point is a mission is by definition requires huge amount of science and technology development, right? It's not one individual kind of science. And the technique that I talked about covers every form of science, understanding the fundamental aspects, which is absolutely necessary. And if you have paid attention to the first talk by Professor Chidambaram, he was pointing out how it is important to understand at a fundamental level to make also technological advances. He gave many examples, including the plutonium, how it would, one phase that is to be avoided and a little bit of gallium mixed into it change that, suppress that phase formation, which is known to the basic because of basic science studies. So also, so there is many aspects of any mission, not only the hydrogen mission, because it will involve wide spectrum of science, will tremendously benefit from use of synchrotron radiation.
Yes, sir.
The next
I
question.
have one more.
Yeah. Okay.
Please
Go ahead. Please go ahead.
Like today we are facing issues like storage of electricity. Like during night times, mostly electricity is not used that much, so it has to be stored in some way. Can this technology be used to solve this particular problem?
Yes, in fact, it's being extensively used. In fact, I'm glad that you asked this question because it shows that you're very aware of some very important issues. The alternative sources of energy, the main concern today is the storage technology. And in storage technology, as you know, batteries are playing a very important role. And batteries, it is necessary to understand, it's a very complex process that goes on inside during the charging and discharging cycle. Most of the time, battery materials have been studied inertly because as the charging and discharging is going on, you couldn't study. Synchrotron radiation allows you to study during charging and discharging what is going on. You can look at how the ions are migrating in space and time, what chemical changes are taking place because you can do chemical sensitive analysis. So you combine all the three techniques that I talked about, diffraction, imaging, and spectroscopy, to understand the charging discharging processes of batteries and therefore figure out what are the reasons batteries fail, what limits their life cycle, what limits their open circuit voltage, etc., etc. And those are the things that can be, there's important contribution that comes from these basic studies.
Any other student?
Yeah. The next question will be by Ms. Sunidhi Sri Prabhakaran. Sunidhi Sri Prabhakaran, you can unmute yourself and ask your question.
Yeah, good afternoon, sir.
Good afternoon.
Sir, I want to ask about synchrotron systems. That you told that in booster, it is moving with velocity of light. So
Nearly the velocity of light.
Like,
Sorry, Sunidhi, sorry. We have to be very precise in science. Don't ever say with the velocity of light. With very close to the velocity of light. Yes,
yeah,
it's very important nearly. For if it is 100 kilometers per hour, you can approximate and say 100 or near, it doesn't matter. But velocity of light is very special. So that's why you need to say nearly the speed of light.
Nearly.
Okay.
Yeah, so sir, if we use, you told that voltage is used for moving in nearly to velocity of sound. So now, so if we use megavolts and if we use that, then we cannot use to move it and move nearly to the velocity of light. So how come is it possible?
The energies of the electrons that you're talking about is giga electron volt. I mean, it's not MeV, but in GeV. The electron energy is in the GeV range. And if you calculate from there, you'll find that it's moving within a fraction of the speed of light.
So in booster,
so they require extraordinary amount of energy. So very often you have dedicated power supplies, of course, for these. Yeah, go ahead.
So thank you, Sunidhi. And due to time constraints, we have to limit this session. And this is actually was turning out to be a great session in terms of discussions. And we believe that such discussions should be a part and should be kept for more times in the upcoming functions, online celebrations. Thank you very much, Professor Sharma. And we really thank you from the Bhabha Atomic Research Center as well as from on behalf of all the students who have joined live. Thank you very much, sir.
Thank you. It's been my pleasure. Thank you and all the best to all of you.
Thank you, sir.
Have fun with the National Science Day. Bye. Take care. Bye-bye.
So students, don't you feel that such a brilliant light can also be available naturally somewhere in some place? The answer is a very big yes. Just watch this fascinating movie prepared exclusively for you on this occasion, which will be followed by another very nice talk by Professor Dipankar Bhattacharya.
Synchrotron radiation is omnipresent in the universe. It is produced when highly energetic charged particles such as electrons and protons spiral around magnetic field lines at a constant speed, and it spans over the entire electromagnetic spectrum ranging from radio waves to gamma rays. Energetic particles are produced in different corners of the universe by some processes still unknown to mankind. When energetic particles enter the magnetic field of Earth, they produce geosynchrotron radiation in radio band. Up in the sky, heavenly objects emit much of their energy through synchrotron radiation. In our Milky Way galaxy, rotating neutron stars with very strong surface magnetic field are born after supernova explosion. They produce pulses of synchrotron radiation due to the spiraling electrons in their surface magnetic field. Beyond the Milky Way galaxy, gigantic jets powered by supermassive black holes at the center of different galaxies show their presence through synchrotron radiation. Atomic Research Center has set up one of the largest gamma-ray telescopes, MACE, at highest altitude in Hanle, Ladakh, to probe the high-energy processes related to synchrotron radiation from various sources in the universe.
With this preamble, I introduce you to yet another well-known figure in Indian science, Professor Dipankar Bhattacharya from Inter-University Center for Astronomy and Astrophysics, Pune. Professor Bhattacharya has several awards, recognitions and novel concepts to his credit in the field of compact stars, in particular neutron stars. Professor Bhattacharya will be live now.
I hope I'm audible and my screen is visible.
Yes, we can see you, sir. Yeah.
Okay, good. So, thank you very much for inviting me to present this lecture. It's a pleasure to be in this company of eminent scientists as well as so many enthusiastic students. And you had already seen in the preceding video that synchrotron radiation occurs ubiquitously and naturally in the universe in many places. I will take you through a few of them, and then describe a few bit of properties which we observe from the synchrotron radiation. Let's get started. By now, you're completely familiar with how synchrotron radiation is generated. If you have a magnetic field and if you have an electron or any charged particle for that matter, which has a momentum which has a component which is perpendicular to the magnetic field, then the electron will execute a circular motion. But if there is also a component which is parallel to the magnetic field, then it will execute this gyrating motion where it spirals around the magnetic field and also moves forward. And in this process, because of the centripetal acceleration, which is produced by the magnetic field, the Lorentz force, the electron will emit radiation. This radiation, if the electron happens to be moving very, very fast, nearly the speed of light, we call that synchrotron radiation. Now, in the universe, magnetic fields are present almost everywhere with a very large range of strengths. Weak magnetic fields of order nanogauss. Now, just to compare, the magnetic field on Earth's surface is about half a Gauss on an average. So, in the vast intergalactic space, the magnetic field strengths are of the order of nanogauss. Inside a galaxy, the magnetic fields, the diffuse magnetic fields, are of the order of a microgauss. From there on to stars and to compact stars like neutron stars that was mentioned in the video, we have magnetic fields ranging all the way up to petagauss. So this is an enormous range of magnetic fields. But what is important is that the magnetic field is ubiquitous. It is there everywhere. So if a relativistic particle, a charged particle, enters any of these magnetic field, then clearly it is going to emit a gyrosynchrotron emission. And that's what is the source of natural synchrotron emission. And we find strong synchrotron emission from many, many places in the universe. Let's recapitulate a few properties of the synchrotron emission. Now, if an electron is circling around a magnetic field, having a gyrating motion, and if this motion is a relatively slow motion with a speed much less than the speed of light, then the radiation it produces is more or less a sinusoid with a fixed frequency, which is related just to the magnetic field. Of course, it also relates to the electron charge and mass, which is a property of the particle itself. So given a magnetic field of 1 Gauss, the frequency of this cyclotron emission, as we call it at this stage, is about 3 megahertz. So if you take an electron and then release it in the Earth's magnetic field, moving slowly, then it will produce a radio emission at a frequency of 3 megahertz. Now, if you have an electron which is moving slightly faster or slightly slower, this frequency will not change as long as the speed of the electron remains far less than the speed of light. However, things change when the electron is given so much energy that its speed nears the speed of light to a great extent. So one of the things that happens if you take an emitter, let's say a dipole, a stationary dipole, it has a radiation pattern. This is intensity as a function of direction, which will have a pattern which is more or less symmetric. Now, if you take this and you move it at some speed in this direction, then relativistic transformations tell you that what will happen is that the emission in this direction of motion will enhance, the emission in the opposite direction will reduce, and the angle within which this emission is emitted forward is reduced. This is what we call relativistic beaming. So if you take this and move it to a speed which is very close to the speed of light, the emission will be beamed almost entirely along the velocity of the particle. And this is what happens when you take an electron and start moving it relativistically in its orbit around the magnetic field. So let's take this arc as being a segment of the orbit around the magnetic field. But the electron is moving relativistically, so the emission from it is confined in the direction of its instantaneous motion with an angle which is 1 over the Lorentz factor of the electron. What is the Lorentz factor? The Lorentz factor is defined as the energy of the electron in units of its rest energy. And this gamma can also be written in terms of the speed of the electron as 1 minus v by c squared, being 1 over the Lorentz factor squared. So as you can see, if the speed is 0, then this gamma is 1. That means the energy is equal to the rest energy. However, if speed nearly equals the speed of light, the gamma can increase arbitrarily, tending to infinity as v tends to c. So as gamma increases, the beaming of this becomes tighter and tighter, and the radiation gets focused more and more in the forward directional motion. So now if you have an observer observing this electron moving in its orbit, then only during the time that this narrow cone is pointing towards the observer will find an electric field from it. At other times, the amount of electric field coming from the electron will be very much lower. So it's electric field as a function of time, then you will get this narrow spikes instead of the sinusoidal profile which we saw for cyclotron radiation. That will get modified to these very narrow spikes with almost no electric field in between. And as a result of this, the spectrum of the radiation will change drastically. Instead of being a monochromatic radiation at the frequency equal to the gyro frequency, it will now be a spectrum which is a continuum spectrum with a very wide range of frequencies, but peaking strongly at a frequency which is now I'm calling it new synchrotron, which is Lorentz factor squared times the cyclotron radiation frequency. Now, as you know, the cyclotron radiation frequency was proportional to the magnetic field, the other things being fundamental constant. So this is also proportional to the magnetic field, the synchrotron frequency, but it now has an additional factor which is proportional to the square of the energy of the particle. So if the electron was moving non-relativistically with speed much less than the speed of light, then if you change the energy of the particle within some limits in that range, the emitted frequency did not change very much. It remained at the cyclotron frequency. However, if you're dealing with relativistic electrons, then the characteristic synchrotron frequency emitted by the particle is a strong function of its energy. So if you increase energy by a factor of 2, the synchrotron frequency will increase by a factor of 2. So now if you have in a source a mixture of particles of various energies, then each of those particles will produce this pattern of emission, but at different scale to different frequencies. So as a result, the overall emission will be a really broadband one. The amount of waveband, electromagnetic waveband, the synchrotron radiation typically tends to cover from cosmic sources is extremely large, starting from radio wavelengths to gamma rays, so practically over the entire electromagnetic band. So that's the basic property of the synchrotron radiation. As we see that you have fast moving particles which enter magnetic field regions and produce synchrotron emission. But these fast moving particles have to come from somewhere. So you need some kind of accelerator to generate these relativistic charged particles. So where are these cosmic accelerators? These cosmic accelerators occur all through the universe in various forms. The most common ones, and some of the most energetic ones also, are shock waves. Shock waves are discontinuities in fluid motion when some energetic phenomenon occurs in a certain region of a fluid, for example, interstellar gas. Example of an energetic phenomenon could be a supernova explosion, which you heard about in the video preceding this lecture. So such an energetic event will suddenly dump a large amount of energy in the medium and raise the local pressure to a very high value. This highly pressurized gas now tends to expand and move forward, and in the process encounters other gas which is around it. But if the pressure is very high, then the front of this gas moving through the ambient medium moves at a speed which is much larger than the sound speed of the medium which is outside it, which is around it. So if any discontinuity moves at a speed much larger than the speed of sound, the material in front of it does not come to know of it, because in the medium, pressure waves would only propagate at the speed of sound. So the fact that there is an enhanced pressure, the information about it propagates in all directions at the local speed of sound, but the front itself is moving faster than that. So therefore, this gas is not even aware that a pressure wave is going to come and hit it. So the discontinuity remains a discontinuity. It does not dissipate as long as it continues to move at speeds larger than the speed of sound. So in such a situation, what you have is behind the shocked gas, which is high temperature, high density, is moving through and impacting gas, which is at lower temperature and lower density. So these are like two different media. And you can think of this as two different media colliding with each other and continuously coming close to each other. Now, in this medium, if you have a charged particle with a sufficiently large speed so that it can cross this medium both ways, then a charged particle like that, since in the medium, since in the medium there are a lot of turbulence, many magnetic structures, the magnetic field is present in both media, but it is not uniform. There are points at which magnetic field is enhanced. That is due to the local density distribution and turbulence and so on. So there could be points from which the particle can get scattered magnetically and change its direction. So let's say the particle starts here and then it gets scattered by one of these magnetic irregularities and gets directed in this direction. So it crosses the shock front, comes behind the shock. Now here is all this material which is moving at great speed in this direction. Now, here also there are such kind of scattering centers. So at some point it will get scattered from a scattering center which is in the shocked medium, which with respect to this medium is moving forward at great speed. So it is like a ping pong ball coming and then getting hit by a forward moving table tennis bat, and so it acquires energy and then gets flung back in this direction, and then it can get scattered again in the upstream medium, come back and scattered again from this forward moving medium, and at each of these scatterings it will pick up some kinetic energy. After many such scatterings, charged particles like that can be accelerated to extremely high energies, very close to the speed of light. So this is one of the common processes by which relativistic particles, electrons, as well as protons and other ions get accelerated in the universe to very high energies. So this is one process which is common and then is also ubiquitous in almost everywhere and successful in producing high energy particles. There are also magnetospheres where you saw in the preceding video a neutron star with a strong magnetic field moving around, and moving magnetic field in such magnetosphere produce electric fields, and those electric fields can accelerate particles. And you also saw in the preceding video material accreting onto black holes, for example. They come in accretion disks, and magnetic fields can be generated in these accretion disks, and then magnetic processes can also act as prolific accelerators of charged particles. So these charged particles, wherever they are generated, they produce, of course, synchrotron radiation locally, but eventually these charged particles are released in the diffuse medium, and they are the ones which we have come to know as cosmic rays. These are fast-moving charged particles, including electrons, which are moving everywhere in the universe. And if you go to space, you find lots and lots of these high-energy cosmic rays, which are present. And they are accelerated in zones like this, and they then move everywhere. And these relativistic particles, as they move everywhere, they generate synchrotron radiation wherever they go in the local magnetic field. So let me give you some examples of places where strong shock waves can be produced. At the end of the life of a massive star, it goes through various stages of nuclear burning: hydrogen, helium, carbon, nitrogen, oxygen, silicon, magnesium, and finally it produces iron at the core, and then it can't burn anymore because there is no fusion possible. Then the core collapses and a lot of gravitational energy is released, which throws out the external envelope with very high speed, up to tens of thousands of kilometers per second. And whereas the interior, the collapsing iron core, then forms a compact object like the neutron star. So this extremely fast moving ejected material then interacts with the diffuse interstellar gas which surrounds it and then drives a shock. And we see objects, many objects like this, which are now present. So this was a supernova that it is in our galaxy. It occurred about 800, 900 years ago. And so what we see now in that place, here is a picture taken in X-rays, and here is a picture taken in radio of the same object. And in X-rays, you see all this hot gas, which was ejected from the supernova explosion, and it is still very hot and at high thermal pressure. It is moving at very high speed through the external medium, and it is driving a shock. And this in green marks the radiation in X-rays that is being produced by fast-moving electrons, relativistic electrons that have been generated near the shock by shock acceleration. And this relativistic electrons are then producing synchrotron emission in the local magnetic field. This green emission that is shown here is synchrotron emission. The rest of it is emission from hot thermal plasma. So here we see synchrotron emission in action. In X-rays, in the same object, if you take a radio picture, you see all this. This is entirely a synchrotron emission. These relativistic particles, which are generated in the shock, now are producing radiation all the way down to radio frequencies. And at radio frequencies, the thermal emission is no longer very bright. So all you see is the synchrotron emission. And these are very, very powerful, very, very bright. Each supernova remnant like this can have a synchrotron luminosity which is 10 times the total luminosity that the sun is producing. The sun is producing a luminosity of 10 raised to the power of 33 ergs every second, or 10 raised to the power of 26 watts. So, so this is a huge amount of energy that the supernova remnants produce in synchrotron radiation alone. And all these cosmic rays, which are now being accelerated here, which are producing this radiation, are also released from the supernova, and they drift through the entire galaxy, and they're available all over the galaxy as cosmic rays. Now, I talked about magnetospheres. So here is an example of a magnetosphere where you have a neutron star, and the neutron stars, when they're produced with extremely strong magnetic fields, typically about a teragauss, going all the way up to a petagauss field. So in a teragauss neutron star, when it is spinning, these neutron stars also have fast spin. They can spin as fast as a millisecond to several hundreds of seconds. And a spinning magnetosphere like this, when you take a bar magnet and spin it, then you will get the corresponding electric field like a dynamo. And that electric field can be extremely strong in pulsar magnetospheres. So these are objects that work as pulsars. So the total electric field that you can generate in these magnetospheres can go up to 10 raised to the power of 15 volts. So an electron can be accelerated to 10 raised to the power of 15 electron volts in this magnetosphere. And of course, therefore, it's extremely relativistic. And given this extremely strong magnetic fields here, it produces very high energy synchrotron emission. And this synchrotron emission, because of this rotation and the beaming that accompanies it, to an observer, every cycle of rotation, for some time the beam is pointed towards you, for sometimes it is not. So you see the radiation for a part of the spin period, and you don't see it for the rest of the time. So it looks like the object is emitting pulses, and that is why we call these pulsars. Neutron stars with even higher strength of magnetic field, petagauss magnetic field, can undergo even other more exotic processes. When you have an extremely strong magnetic field like petagauss field just subsurface, it is almost strong enough to cause disturbances in the crust of the neutron star, and from time to time such disturbances happen. The crust cracks, and then the cracking of the crust causes a large agitation of this magnetic field, and this extreme agitation of the magnetic field produces corresponding electric field, and those electric fields can produce very energetic electrons, and those electrons then doing synchrotron radiation gives rise to very bright emission for this short while until this lasts, the effect of the crust cracking lasts, and then it dies down again, and in future it would crack again somewhere else, and again it produces a burst. So these are called magnetas, and this is called a pulsar. I'll show you an example of synchrotron emission in X-rays, high energy X-rays, that one such pulsar can produce. This is a pulsar called the Crab pulsar, and this is an observation from our X-ray observatory, Indian X-ray Observatory Astrosat. So you can see how regularly the pulses arrive. Every pulse does not look exactly the same, but it has a basic average property, and you have a strong emission that you can observe easily from such pulsars. The synchrotron luminosity of such pulsars can exceed about 1,000 times the luminosity of the sun. This Crab pulsar that I was talking about it generates these relativistic particles which produce this pulsar emission in its magnetosphere. But having produced that emission, the particles stream out and then inhabit its surrounding. So this crab pulsar was produced in a supernova explosion, and the debris from the supernova explosion is still lying around it, and which creates a cavity. The fast charged particles, which now take the form of electron-positron pairs, emitted from the pulsar, then fill this cavity. And this is an optical image taken by Hubble Space Telescope. You can see these filamentary emission, which happens to be the material left over from the explosion. But inside, you see a very diffuse blue glow, and that comes from synchrotron emission created by the charged, relativistic charged particles emitted by the pulsar. And that part of it is visible at the entire electromagnetic band. This is an infrared picture where also you see part of these thermal filaments. But you go to other wave bands, the thermal component does not contribute very much, but you begin to see the synchrotron component alone. This is far ultraviolet, near ultraviolet. This is X-rays, and all this is entirely synchrotron emission. The synchrotron luminosity of this nebula exceeds 10,000 times the luminosity of the sun. And I talked about the crust cracking of magnetars. So in such events, the magnetars can produce these hyperflares. This is one of the hyperflares observed on 27th of December 2004 from this object, which is called soft gamma repeater 1806-20. The peak luminosity, which lasted for a fraction of a second, was 1 trillion times that of the sun. And then, of course, it settled down. And then after a while, after a few hundred seconds, the emission died down to a much lower value. But when it goes off, it can be extremely bright synchrotron emission. You already saw in the preceding video that one of the prolific emitters of synchrotron emission are galaxies in which there is a central supermassive black hole, and this supermassive black hole is being fed large quantities of material from the gas in the surroundings. So if you have a supermassive black hole and the gas comes in, spiraling in and falls into the black hole, in this gas that is spiraling in, magnetic field can be created. And this magnetic field then has processes which can extract energy from the black hole. If the black hole is spinning, then the spin energy from the black hole can be extracted, and that electromagnetic process can then give rise to highly energetic relativistic particles. And these relativistic particles get trapped in the helical magnetic field, which is caused by the spin of this accretion disk, and then they get collimated and produce very large jets. And some of this acceleration process can also happen due to the reconnection of the magnetic field between the magnetic field threading the black hole and the magnetic field threading the accretion disk. And through that, you can get reconnection processes which can also accelerate particles to very high energies. So there are objects which produce extremely high amounts of synchrotron emission through this process, and objects like these are called active galactic nuclei, and they include varieties of objects which are called radio galaxies, quasars, blazars, and so on. And here is an example of one such object. You have the source of relativistic particles at the center over here, and then these large jets of relativistic particles. They're so energetic that they can move millions of light years in this form and then interact with the intergalactic medium. And having done so, there is a shock here, and then the particles backflow, and they accumulate over here, and they produce bright lobes of synchrotron emission. All that you see here is synchrotron emission seen in radio wavelengths. The synchrotron luminosity of these objects can be 1 billion times that of the sun, and these objects continue to produce this radiation for millions of years. So these are one of the most prolific sources of energy input from the black hole and the accretion process into the surroundings. Now, some of the supernova explosions that I mentioned can also be accompanied by such accretion disks at the center if a black hole is formed at the center. And a similar process can produce a fast-moving jet. And this fast-moving jet, if you happen to be looking down the throat of the jet, then you can see a very bright explosion, as you saw in this over here, where this is the map of the entire gamma ray sky. And at the peak of this explosion, the gamma ray emission from such an object can completely overwhelm the entire sky. It can outshine the entire gamma ray sky total emission from all sources put together. But these objects, these events are known as gamma ray bursts. They happen during the late stages of this supernova explosion. Could be due to the collapse of a massive star, or could be due to merger of two neutron stars. And the peak synchrotron luminosity in the gamma ray burst is an incredible 1 billion trillion suns. These are the brightest, most luminous synchrotron sources that we know about. Of course, they don't last long, they last only a few seconds. But when they last, they produce the brightest synchrotron emission that we have seen so far from any object. So now all these acceleration sites, the cosmic accelerators, which I went through in the previous slides, produce large quantities of these relativistic particles, and then the relativistic particles then are free to move around everywhere. In our galaxy, for example, these relativistic particles are there everywhere, and the magnetic field is also present. And the relativistic particles moving through this magnetic field produce a diffuse emission all through the galaxy. So this is a map of our own galaxy at a radio wavelength of radio frequency of 408 megahertz. And you can see the distribution of radio emission. This is the galactic plane, the Milky Way galaxy, as you know. And but it is emission is there everywhere. This is produced by cosmic rays in the galactic magnetic field. The magnetic field itself has a strength only of about a microgauss on an average in the galaxy. So one of the properties that I would like to touch upon of the synchrotron radiation that we see from in the cosmic setting is that its spectrum. So these acceleration processes that I mentioned, either the shock acceleration or the acceleration in magnetospheres where pair cascade can occur. So you take a charged particle, accelerate it, it produces radiation. The radiation then produces electron-positron pairs. Each of the electron-positron pairs then produce further synchrotron radiation, which photons and again produce further pairs and so on. So you get larger number of particles as you cascade down to lower energies. And similarly, in shock acceleration, you get you take a certain number of particles, and then by multiple crossings, you boost them to higher and higher energies. But at each stage, there is some amount of particle which it does not go further to the next stage of acceleration. So fewer and fewer particles go to higher and higher energies. So both these processes produce typically a power law distribution of particle energies. The number of particles at a given energy E is proportional to the energy to the power of some minus some power P over here, which is a number which is close to 2 in most cases. So if you have a particle energy distribution like this, the synchrotron emission from it would be, again, a power law distribution in intensity as a function of frequency, and with a index, this is a log-log, so it's a straight line in log-log with a slope of minus p minus 1 by 2. So you then have a distribution which looks very different from the spectrum that we would, for example, see from a star or any other hot body, which is a thermal radiation, where there is a characteristic frequency, which is equal to kT over Planck's constant, and the radiation falls off on either side of that characteristic frequency. It goes to a peak. But this power law spectrum doesn't have any such feature. So it's scale independent, and as a result, it tends to have excess emission compared to any thermal emitter at both the high energy end and at low energy end. So when you go to low frequencies like radio, most of the sources you see are synchrotron dominated sources. When you go to very high energy end at hard X-rays and gamma rays, again, most of the sources you see are dominated by this non-thermal emission. So the synchrotron emission itself tends to be much more broadband than thermal emission. So if you take a overall spectrum of a synchrotron emitting body, the power law part that I mentioned occupies large fraction of the spectrum, minus p minus 1 by 2. Now, if there is a lower limit to the Lorentz factor of the particles that have been accelerated in the accelerator and which are available for radiation, let's say the synchrotron frequency corresponding to that is over here, then at frequencies below that, you would see a drop off with a slope of plus 1/3. Now, the synchrotron process, which is an emission process, has its own inverse. So every emission process has its inverse, which is an absorption process. So if you put sufficiently large number of particles together, then the synchrotron photon emitted by one particle can be absorbed by another particle, and that particle moves to a higher energy state or higher momentum state around the magnetic field. So that's called synchrotron self-absorption. And the amount of absorptivity goes up as you go down in frequency. So at lower and lower frequency, the absorption probability increases. So as you start from high frequency and you keep going down in lower and lower frequencies, at some point, absorption may become important. Now, if the absorption becomes important at a frequency which is higher than the lower limit that I talked about earlier, then the radiation will be absorbed over here, and you will get an absorbed synchrotron self-absorbed source with a slope here of plus 2.5. If it happens to be at a frequency which is lower than this, then you will get a you will also get a drop, but here the slope will be plus 2. I'll not go into the reason here as to why there is a difference between these two cases, but this is important. Now, the frequency at which this absorption occurs, or the frequency at which the peak of the synchrotron emission is reached, is dependent on the population of the particles over here in the emitting source and its magnetic field. However, the total luminosity of the synchrotron emission is also dependent on the particles in the source and the magnetic field. Now, if you have a measurement of both these quantities, the total luminosity as well as the frequency at which the absorption is occurring, then using these two measurements, we can actually find out what is the magnetic field in the source and what is the population of particles, how many particles are there of what kind of energy in the source. So this gives us a diagnostic of the synchrotron source. Now let's go to the higher energy end of the spectrum. The particles, as you have noticed earlier, have a energy emission rate which is proportional to the square of the energy. So the power radiated by a particle is proportional to the square of the energy. So the rate of emission of energy goes up faster than the energy itself of the particle. So above a certain energy, then the amount of energy emitted by the particles are dominate, and the particles lose most of their energy by synchrotron emission, and they become tired. And even if you had injected an energy spectrum which would have produced a power law spectrum of -p minus 1/2 to a larger range of frequencies, because the particles get tired, their energies go down, the spectrum steepens. So this is called a break frequency. And the longer you leave the source in the same fashion, the more such particles will lose their energy, and this break will keep moving downwards in frequency. So the break frequency then depends on the age of the source. So we have from this the measurement of the number of particles in the system, the energy of the particles, the magnetic field, and if you also measure this break, then you can also measure the age of the source. So the synchrotron emission offers us all these different tools by which we can characterize the properties of the source. The last thing that I would like to say about synchrotron radiation is that the synchrotron radiation is strongly polarized, which you also heard in previous lecture. In the cosmic setting, the polarization fraction can go up to 70% with a polarization angle which is normal to the projected magnetic field in the sky. So if you see synchrotron emission with a certain polarization angle, you know the magnetic field at which the emission is occurring is perpendicular to the local to the polarization angle that you see. So you can use this for mapping the magnetic field in galaxies. So this is an example of a galaxy called M51, where the radio synchrotron emission, the polarization of radio synchrotron emission, has been used to derive these vectors, which you see here. And these vectors represent the local magnetic field. So as you can see, this is a spiral galaxy. The magnetic field tends to be aligned along the spiral. This is this observational derivation of how the magnetic field is distributed in the galaxy. We can also measure the strength of the magnetic field of these in these galaxies through another property of polarization, which is called Faraday rotation. So as radiation moves through this magnetic field at different frequencies, the polarization angle is rotated by a different amount. And that depends on the resonant frequency in the magnetic field. So therefore, the amount of Faraday rotation which you can measure by observing the polarization at multiple emission frequencies, we can use that to find the strength of the magnetic field through which the radiation is moved. So through the study of the polarization, therefore, we can find both the geometry and the strength of the magnetic fields. So synchrotron radiation again offers us this opportunity of studying these various properties of various cosmic sources, including galaxies. So I will summarize what I have said so far. It is the synchrotron radiation is a common phenomenon in the universe. It's produced by relativistic electrons in the local magnetic field. Magnetic field is present everywhere in varying strengths, and relativistic electrons are accelerated in high energy locales, such as shocks, pulsars, magnetars, accretion disks, etc. There are also these locales also happen to be strong emitters of synchrotron radiation. And these relativistic particles, once accelerated, they disperse widely in the form of cosmic rays, generating diffuse synchrotron emission everywhere in the universe, in practice. The synchrotron radiation typically occurs over a wide range of electromagnetic wave bands. The spectrum and the polarization of synchrotron radiation can help us infer the source properties, including their age and the magnetic field distribution. So I will stop there. Thank you.
Thank you very much, Professor Bhattacharya. We have time for one quick question. If any student wants to ask some question in WebEx, they can raise their hand.
Yeah, there is one question from Ayaz Khan. Ayaz, you can unmute and then ask your question.
Professor Bhattacharya, you can stop sharing your screen now.
Yes, sir. My question is about exoplanets. So we know that the planet has its own magnetic field, and greater will be the planet, stronger will be its magnetic field. So alpha and beta particles coming from a star come in the influence of the magnetic field of any bigger planet and strike its atmosphere. So will it emit electromagnetic radiations, and by observing it, can we get the information about the atmospheric structure of the planet?
Yes, it is correct. So many of the exoplanets are observed in radio, and these radio emissions produced by charged particles, electrons in particular, coming from the nearby star and going through the magnetosphere of the planet. In fact, this happens in the Earth as well. So you saw in the video talking about geosynchrotron emission. So there are synchrotron processes as well as cyclotron major processes which produce emission. And closer to the planet's atmosphere, these particles interact with the magnetosphere and then produce excite the atmospheric atoms. And you can get optical emission like the Earth's aurora. So you can see that also from exoplanets. So yes, this can be used to probe the atmosphere of the planets as well as its magnetosphere.
Gargi Ajay. Gargi Ajay, ask your question.
Hello, sir. Good afternoon.
Hello.
Sir, I had a question that today we came to know synchrotron radiations produce massive energy. So, can this energy and light as well? So, can this light energy be used in countries like Norway, which live nearly half the year without sun as a source of energy?
Well, these are huge quantities of energies are produced in these sources, of course, but these sources are not nearby to us. So by the time we receive the radiation, we receive a very small quantity of energy. So that is the energy received from astronomical synchrotron sources is not of a significant quantity to power our daily needs. The sun, although it is not as prolific an emitter as I've said that some sources produce even billion times the sun, but sun is much closer to us. So the amount of energy we receive from the sun is much, much more than what we receive from the other objects. So no, so far I don't think there is any practical solution for energy that can be derived from the astronomical sources. It is better for us to try to utilize the solar energy which we do have.
Mr. Sunil Bull. Sunil Bull, you can ask your question.
Hello.
Sir, as you had said that realistic that charged particles needed to produce the synchrotron emission, yes sir. And what if we use that uncharged particles? Can we accelerate that uncharged particles too?
No, uncharged particle, of course, will not feel the acceleration due to the Lorentz force. So the uncharged particle will not gyrate, uncharged particle will not be accelerated. And an uncharged particle, even if it accelerated, does not produce electromagnetic radiation. So it is not something that will come into discussion in this context. So I'm not sure exactly what you have in mind. An uncharged particle, but atoms, if you happen to have atoms, which overall uncharged, but it consists of charged particles. So such atoms, if charged particles which are accelerated like this impact such atoms, then that atom can be excited to produce radiation. But otherwise, particles which are really uncharged, like a neutron or something like that, will not participate in the synchrotron radiation.
Mr. Mayank Gulati, you can unmute and ask your question. Mayank Gulati, you can ask your question. Otherwise, Rahini Mahobe, you can ask your question. Ragini.
Hello.
Good afternoon, sir.
Yes, go ahead.
Sir, can we use synchrotron radiation in the purification of that land that are totally polluted from non-biodegradable waste?
Yeah, so laboratory generated synchrotron emission can be used for various things, but industrial scale use of synchrotron radiation in waste processing is not something that is being currently done, but I think there are other experts in the audience who can answer this question better.
Okay, thank you, sir.
So this interactive session is indeed coming out to be a great event, and we should really follow this in future course. Thank you, Professor Bhattacharya, for this wonderful presentation and interaction and joining us from Pune. Thank you very much.
Thank you very much. My pleasure. And have a fantastic workshop. Thank you very much.
Thank you very much. With this, we come to the most exciting event of the day for the students, and we had a quiz session. Before describing about that, I would like to invite our expert panel onto the dais. Dr. T. Sekuntala, who is the head of the High Pressure and Synchrotron Radiation Physics Division of Bhabha Atomic Research Center. Dr. S.R. Jain, the expert in nuclear physics. Dr. Debashish Sen from Solid State Physics Division of BARC. Dr. Subir Bhattacharya from Astrophysics Division of BARC. And we also have Dr. S.N. Jha sitting live at the synchrotron in Indore, who will be who will also be joining in this quiz session. So the modalities of this quiz session were, because of the online nature of the program, we had to restrict it to few rules and regulations, and we sent the questionnaire to the students one day before, and we received the answers, and the response was really overwhelming. And due to the time constraint and the nature of the event, we'll not be able to show all the students who have responded, but those students who gave the maximum number of correct answers and faster than any other student. In this, so I request Dr. Sakuntala to please take over the quiz session from now, and we'll open the questionnaire, which will be displayed onto the screens also. Okay, Raman, can you
Good morning, everyone. Thank the organizers for factoring in this very interesting session. Interesting in the sense this quiz program simultaneously tests two things: the students, how well they have understood, and the teacher or the speaker, how effectively they have communicated. So indeed, it's a very interesting session. Even I'm quite excited to see how many people have given what spectrum of answers. So with these words, I welcome everyone to the interesting session. Let's start. There are about 20 questions communicated to the students, I understand. May I know how much, how many students participated and how many have given the correct answers?
How many have given the correct answers? Not exactly. 142 you said. 100, maybe 180 roughly.
180.
180, yeah.
Okay, I'm so happy to know that about 180 students have participated in the quiz. And how many students have given all the answers correct?
Around 3 students. So, 5 students.
Oh, 5 students out of, okay, that's very interesting. Shall we go through the question one by one?
Yeah.
Yeah.
Good afternoon, everybody. I have joined from Indore.
So this was Dr. S.N. Jha who was speaking live from Indore. So we'll go. We have selected first a few representative questions which require a bit of discussion in terms of fundamental understanding of the subject. And based on these selected questions, we'll go each question one by one, and try to explain the students the concept and the answers behind the concept behind the answers and the answer as well. So the first question, which is prompted on your screens, is which wavelength ranges are generally produced by the synchrotron process in different astrophysical sources? Yeah, you can speak.
Well, the answer of this question is the fourth one, that is the radio, optical, UV as well as X-rays. Now the question is why? See, already you people have come to know from the previous lectures as well as the movie that when a charged particle gyrates around a magnetic field, then it emits synchrotron radiation, and the emitted radiation energy, it depends on the energy of the particle. Now, in our accelerator, in synchrotron, generally we generate monoenergetic particles which emit radiation. But in case of a cosmic accelerator, that is the accelerators which are accelerating particles in nature, there we cannot control the energy of the particles. They are completely decided by the ambient conditions. And particles can be, produced with a wide span of energy. And such energy, energetic particles over this wide range of energy, they can produce wide range of synchrotron photons, thereby giving a spectrum which vary over this energy band from radio to X-rays, and in some favorable conditions it can give even gamma rays. Okay, fourth option of the question is the correct option.
Okay, thank you, Dr. Bhattacharya. Now we go to the next question. If V1 is the speed of 16 keV X-ray and V2 is the speed of 4 keV X-ray in vacuum, then which option is correct?
Okay, so let us discuss this. From the today's session, I think all of you have understood that the synchrotron radiation is an electromagnetic wave, and you know that in vacuum it is some kind of light, so the velocity for the 16 kV as well as this 4 kV will be same. I will give some analogy like this. Like you and your friend, if both of you are just moving on a road with the same speed, but both of you have one stick in your hand and you are rotating the stick. You are rotating the stick faster than your friend. That does not affect your speed with which you are moving. So your speed can be same, but your frequency, that means the faster or slower you are rotating the stick, can be different. So this is the property of the electromagnetic wave, and that's why in the vacuum their speed will be same in both the cases, although their energy is different, but their frequency will be of course different.
Okay. Thank you, Dr. Sen. The next question in line is, the polarization of the X-ray synchrotron radiation is, so this was a tricky question. I'll ask the panel to.
Okay, this is a tricky question, as Dr. Himal Bhatt has mentioned. So let us try to understand this. So in the synchrotron, what you have already understood, that an electron bunch is rotating in a ring. So let us see, this is the ring. I have something in my hand, I think you can see. It is rotating in the ring, electron bunch is rotating. And when you are looking just in the plane of the ring, so let us say electron is moving like this, and exactly in the plane you are looking, what you will see from this, that it is moving along this diameter, and you will see only a straight line coming this side and this, so it will be linear. This is some kind of analogy I am trying to give, escaping the mathematics. So in this case you will get exactly linear. polarization of the X-ray beam, what you are getting. But if you just look just little top of it, what you will see? You will see that you can see that it is rotating in a elliptical, or if you go very far, you will see almost like a circular one. And if you go down, you will see similar elliptical or circular path again, but it will be in opposite direction. So the polarization of the X-ray in the plane of the ring will be linear, and when you go above, it will be elliptical, and at higher height it will be something like circular, and below also it will be elliptical and circular, but in opposite direction.
Yeah. Thank you, Dr. Sen again. Next question is, when an electron of rest mass m0 moves with a speed nearly equal to but less than that of light, means nearly equal to that of light, then the mass of the electron becomes, so we have the four options.
So this is of course much larger than the m0, which is called the rest mass of the electron. Now this question is connected to one of the greatest thoughts of last century of modern. The force and see how well it can be accelerated. So how does the velocity change in a given interval of time? Now what happens is that the measurement of force and therefore the measurement of mass is therefore intimately connected with measurements of distances and times. Now all these things get mixed up. Distances become smaller if you look at a frame, if you look at an object which is moving at a certain speed, and this is called, there is a factor by which they get smaller. Similarly, the mass gets larger by the same factor, by the inverse of that factor, which is like 1 over square root of 1 minus b square by c square. Now, there is some mathematics which gives us this, but let's try to understand what happens if this doesn't happen, if this is not allowed, if mass doesn't increase. If mass doesn't increase, then let's imagine that there is a spacecraft which is being pushed by rocket motors. If mass does not increase and the rocket motors go on providing its energy and the force to the spaceship will go on increasing its speed and eventually the speed will increase the speed of light. It will cross the speed of light in vacuum, which is not allowed. It cannot happen. So what happens is that as the rocket motors give power to the spaceship, the mass increases. The mass increases and it make the motors more and more difficult for motors to accelerate the object, and therefore as mass goes on increasing, for example, if the speed is such that there is a contraction of the spaceship by a factor of 10, that becomes 10 times smaller, the masses become 10 times larger, and therefore the motors find it very difficult to now change the speed of this massive object by the same amount as it could if it was at rest. Therefore, mass must increase if the body is increasing, if the body is moving at a speed as it goes closer and closer to the speed of light, the mass goes on increasing, gets infinitely harder for the rocket motors to increase the speed anymore. And if this does not happen, it will violate they postulate the special theory of relativity, which says that nothing can move faster than speed of light in vacuum. And therefore, there is a factor which comes from some maths, but the basic idea is that there were two ideas. Weighing is a bad idea. The next idea is you apply a force, and then you look at how the velocities change over a period of time, and from there you infer the mass, which is called the relativistic mass. So mass must increase, and as the electron's speed gets closer and closer to the speed of light, the mass becomes much larger than the rest mass. So I hope that excites you to learn about Einstein's theory.
Thank you very much, Dr. Jain. Next question is, if in one case a thick lead block, is in the path of synchrotron X-ray, and in another case an aluminium block of same thickness is kept in the path, then what happens? I'll divert the question to the panel to explain.
Dr. Jha.
Okay, Dr. Jha, Dr. S.N. Jha from Indore.
Hello.
Yeah, we can hear you, sir.
Yeah. So I think this question number 14, and as well as question 15, both are related. I mean, so I can take up both if you want. That is, 15 is which of the following material will you use as X-ray transparent windows?
Okay,
right?
fine.
Right?
Yeah.
Or shall I take up this one? Okay.
Yes.
So,
Please.
as you know, this the absorption of X-rays in a material is directly proportional to the atomic number and the density. If let us say if you keep the energy constant, let us say we have taken a copper K alpha roughly around 9 keV, let us say. Okay. Now keeping the energy constant. So if you have a high jet, that means a lead, so definitely it will have more absorbing power. And if you have a low jet like aluminium, which has a atomic number of 13, and lead has 82, okay. So definitely we expect that lead will absorb the X-ray, and aluminium, which is a thin, low density material with a low jet value, so it will be transparent. So that's why question A first answer says lead block will allow to pass most of the X-rays. That is not true. So it will not allow to pass most of the X-rays. Basically, it will absorb most of the X-rays. And the second option is aluminum block will stop most of the X-rays. So that answers, since it is a low jet and low density, basically it is a proportional to the jet to the power 4. So that's why this also is ruled out. And that's why both the blocks will serve the same purpose. That is opposite. This is opposite basically answer. So that's why none of the above is true in the case of synchrotron X-ray. If we are having a thick lead block or a thick aluminum sheet in the path. Okay. So this depends. This also is correlated with this Mosley law. You must have heard. So that is the frequency of X-ray coming out of the material directly proportional to Z. So based on that, we can, I think now you understood that why all the three, that answers are wrong. So basically answer will be that lead will be most suitable for absorbing the most of the X-ray. Similarly, is it okay this question answers or
yeah, fine. We can go to the next question.
So no, next question is which of the following material will use as X-ray transparent window? Now here the purpose is, for example, you'll be hearing the next lecture or maybe in the video, that our objective here will be to make transparent most of the X-ray which is coming out of the synchrotron to use for our experiment. So since beryllium has very low jet, low density, so beryllium is only having the atomic number 4. So definitely most of the X-ray it will transmit. So that is our purpose. We want to make transparent for most of the hard X-ray, let us say from 4 keV and above. and below that we want to get absorbed. That means soft X-ray. So that's why beryllium is most suitable. So answer beryllium is correct. And other three like molybdenum, aluminium, and copper, these are all high jet material, high density. So it will absorb most of the X-ray. Okay, is it okay? Or any doubt is there from students? Okay.
No, actually, right now we are not allowing the students to ask directly on this, but yes, tomorrow they'll definitely be there. So thank you for answering these two questions. We now move to the next question in line. Can X-ray synchrotron radiation in reality be produced in a linear accelerator? Justify your answer by proper reasoning is the question. I divert this question to the panel again.
From the morning lectures, you might have heard that X-rays of a given wavelength can be produced by different methods. What is unique to a synchrotron X-ray is there are various parameters. First among them is brightness, very low divergence. There are associated properties which is not the case. True to its name, LINAC, the electric field is in a linear direction. So, the LINAC cannot be used to produce an X-ray synchrotron radiation. Is it convincing?
Yes, yes. Yes. So, with this, we move on to the next question, which is which of the following statement is true? The following four options are X-rays can travel in vacuum with the same velocity as the visible light. Second option, X-rays can bend its path in an electric field. Third option is X-rays can bend its path in a magnetic field. And fourth option is none of the above. So this question itself is a comprising of four questions, I guess this, and I divert this question to the panel.
So the option A is the right answer because the reason is simple. The visible light is an electromagnetic radiation and X-ray is also electromagnetic radiation. And the speed of electromagnetic radiation in vacuum is, we know, c. So X-rays and the visible light both will propagate with the same velocity. That is the c, 3 into 10 to the 8 meter per second. So that is the answer of the question.
So with this, I thank you, the panel, for discussing the questions of quiz. And can we have the names of the winners also in this? Okay, so we have the winners here. Pritish S. from Maharshi Vidya Mandir Senior Secondary School. Subramaniam Garimela from Doon University. Oh. And third is, there are two persons in third and as third winner. First is Shreyash Karanjikar from BK Birla College, Kalyan. And lastly, we have Ashmita Anand from Atomic Energy Central School number 1 from Anushakti Nagar. So with this, I thank you all, and especially I thank the panel experts for joining and clarifying the doubts of the students. We again will have such an interactive session tomorrow as well as day after tomorrow, which will be entirely based on the questions sent by you all the students to the organizing teams. And if we are working out on the logistics, that if time permits and everything goes well, you will be allowed to ask your question live on air, whichever question is chosen. So with this, I thank you all. Thank you. I thank the panel. I thank the students who have joined live. Also, all those who have joined through the internet. And we close today's proceedings for the National Science Day celebrations. And I see you all And we all will be eagerly waiting to again see you all in the morning tomorrow at 10 o'clock sharp. The program will commence and we will be building up on the concepts tomorrow, and you will be enlightened with various aspects of this brilliant field. That's what I can say. Thank you very much, and we leave for now. Thank you.